Jenderal Sudirman, terpatri semangat di dalam dada, unggul dan berkarya sepanjang masa, kembangkan perdesaan berkelanjutan dengan sains dan teknologi.
Okay, now we will enter the plenary session 1, which will be moderated by Mr. Roy Andreas, PhD. But before we enter this plenary session 1, I will read the CV of our moderator, Mr. Roy Andreas, PhD. Mr. Roy Andreas, PhD, was graduated from University of Toyama, Japan for his PhD degree. Now, he is a lecturer in Jenderal Sudirman University who focused on inorganic chemistry. So, for Mr. Roy Andreas, time is yours.
Okay, thank you so much for the Master of Ceremony. Can you, how about my voice? It is clear or not? I'm sorry. My voice is clear or not? MC?
Yes, it is.
Yes, it is.
Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. Good morning, Professor Suyin. Good morning, Professor Won Kuli. Good morning, Associate Professor Dadan Hermawan. And good morning, all participants in the 16th Joint Conference on Chemistry 2021. I really hope everyone present here in good health. As all we know that COVID-19 pandemic is being faced of the whole world until now. So we hope that this pandemic will be end soon. On this Sunday morning, please allow me, Roy Andreas from Jenderal Sudirman University, to be a moderator for the Plenary Session 1 at the 16th Joint Conference on Chemistry 2021. On this occasion, we will have the great opportunity to listen a presentation from three experts on their perspective field. First is Professor Suyin from Tohoku University. And then the second is from Associate Professor Dadan Hermawan from Jenderal Sudirman University, Indonesia. And then the third one is Professor Won Kuli from Sogang University, Korea. Some information I need to pass on before we start. Number one is all keynote speaker will present the presentation about 50 minutes. Okay, 50 minutes. And then number two is after all the keynote speaker presentations, 25 to 30 minutes will be allocated for the discussion. So that means discussion is 25 to 30 minutes. Number three is during the speaker's presentation, please, all the participants must turn off or mute all the microphone. And then the four is during the discussion sessions, participants who want to ask questions, raise your hand, or you can write the question on the chat column. First, state the name, affiliation, questions, and then who is the question for in the chat column. Okay. Before we starting for the first presentation from the Professor Suyin, Tohoku University, so please give me a time, a minute to read his brief profile. Professor Suyin from Tohoku University, Japan. He got the bachelor degree in Inorganic Chemical Engineering from the Dalian University of Technology, master degree in Chemical Metallurgy from the Institute of Chemical Metallurgy, or ICM, latterly Institute of Process and Engineering, IPE, Chinese Academy of Science. And then in 1992 is the first time for Professor Su Yin come to Japan, something like that. And then as a research fellow, 1992, and then to join with the Institute of Chemical Reaction Science, ICRS, or Professor Sato Group in Tohoku University during 1995 to 1997. And Professor Su Yin got the PhD degree in Applied Chemistry from Tohoku University, 1999. And become a lecturer and associate professor at the Institute of Multidisciplinary Research for Advanced Material, IMRAM, Tohoku University in 2005. And then the full professor is in 2016. His research paper were cited more than 12,000 times. 12,000 times. And then citation H index is 62. He also acts as a session chair in more than 30 international conferences. Also, he invited as independent review and referee for more than 40 academic journals. He has authored more than 440 original research papers, including more than 100 papers. More than 100 papers have impact factor more than 4. He also contribute for 25 book chapters or review papers and 22 patents. Okay, maybe this is the brief profile of Professor Su Yin. And to shorten the time, let us listen the presentation from him with the research entitled Development of Environmental Responsive Ecomaterials Based on Isothermal Reactions. Professor Su Yin, now time is yours. Please.
Good morning. Thank you very much, Mr. Dr. Roy. Thank you very much for your nice introduction. And at the beginning, I just like to thank Dr. Anu Liapartora and Professor Wee Sulaiman and other organizer committee members for inviting me, for giving me this chance to introduce my recent research here. And also, I think this is a very wonderful joint conference of the chemistries. From the beginning, I just feel this is a very well-organized meeting. It is very happy for me to join this conference. Okay, let me show my presentation files. Okay. So I think it should be no problem. It is okay.
Yes, Sensei, it's okay.
Okay, okay. It's my happy to join this conference and have chance to introduce my talk. The topic of my talk is the development of environmental responsive ecomaterials based on isothermal reaction. And at the beginning, I just showed the concept of my research. I'm focusing on the development of environmental responsive materials and their application for human life, health, and the environment. Here just shows one of the concept of mine. You can see the solar light spectra here. As we know, it consists of about the UV light, the visible light, and the infrared light. And my research is focused on the functionality of the materials, just related to the different wavelengths of the light, such as in the area of the UV light, I'm studying under anti-UV light materials, and it can be applied as the cosmetic products, and also the application for prolonging the lifetime of the organic materials, and also related to the visible light regions. I'm focusing on the photocatalyst materials, and later I will introduce in detail, and also about the infrared light areas. I'm also studying under smart window materials, and also related to the infrared thermal survey application and something like that. And today, because of the limitation of the time, I just focused on part of my research. Here is the outline of my talk. It was divided into two parts. The first one is the process design. I will focus on the sulfur thermal reaction and also introduce a novel WCISP process. It is also a sulfur thermal process, and it is developed by our laboratory. And to the second part, I just focused on the functionality of the eco materials, mainly focused on the visible light, focused on the photocatalyst materials, then the infrared light shielding materials. And also I will introduce something about the morphological control of non-oxide-based materials. And finally, if I have time, I will introduce something about the gas sensing functions utilize the two-dimension layered compound materials. Okay, let me go to the first part, the process design. And here I just show you three examples for why we want to control the morphology and the particle size of the inorganic materials. Here we can see the case of the zinc oxide. It can be synthesized by a different method. It is reported that by solution process, it is easy to control the different morphology of the particles. And also it is found that the room temperature photoluminescence properties of the zinc oxide changed greatly with the different morphology. This is the first case. And the second example is the gold nanoroad. If you control the particle size, control the morphology, control the aspect ratio of the gold nanoparticles, you can see it will shoot different color. In other words, if you control the morphology size and aspect ratio, you can design the light absorption with different wavelengths. And the third example is a quantum size effect of the semiconductor. It is known that the band gap values will be changed depending on the particle size. In the case of the size is less than 10 nanometers, the band gap values will be increased a lot. So these three examples just show why we want to control the morphology, control the particle size, and something like that. We can control the physical and chemical properties of the materials by controlling these factors. And in order to synthesize the different materials, of course, many different kinds of methods could be utilized. In some cases, the high temperature process, or some cases, the high pressure process. But we are focusing on the environmental friendly solution process, as we can see here, because the solution process could be operated at comparatively lower temperature and low pressure. So in other words, this process is an environmentally friendly process. And in our laboratories, I'm already carried out the experiment under hydrothermal and sulfur thermal process for more than 30 years. Actually, here let me introduce the hydrothermal and the sulfur thermal process simply. Actually, it is developed more than 70 years before. And in 1984, a famous professor, Professor Somir in Tokyo Institute of Technology, who introduced the hydrothermal process in the material synthesis. And he classified the hydrothermal process into 5 categories. The first one is a hydrothermal oxidation. The second one is a hydrothermal precipitation. And the third one is the hydrothermal synthesis, and then the hydrothermal decomposition, and the hydrothermal crystallization. And at the beginning, the solvent, the water was utilized as a solvent. And after that, many different kind of solvent was also introduced into the reaction. And in 1994, the first international conference on silver thermal reaction was carried out in Japan. And from then, the silver thermal was the concept of the silver thermal was proposed by the very famous Professor DiMaggio in France. And actually related to the hydrothermal and the silver thermal, there are many different, many international conferences was held in the past, such as the first hydrothermal process was held in 1982 in Japan, and then in different countries in the world. And in 2006, the International Silver Thermal and Hydrothermal Association was established. And after that, every 2 years, there is a Asia conference held in the world. And 3 years before, as the chairman, I also organized the Asia 2018 in Sendai. And this year, the conference will be in Mexico, but it is decided to carry it out online. It will be next month. So if you are interested, you can visit this website to get the related information. Okay, because the water is the most utilized solvent in the hydrothermal and the silver thermal reaction process. So here, just to show you the physical properties of the solvent of the water, you can see the most important parameters of the water is the ion product and the dielectric constant. We can see they are changed greatly and the high pressure and the high temperatures. Here, the left side just shows the Kw, the ion product. It is related to the reactivity of the solvent, and the right side just shows the electrical constant of the water. We can see the change greatly. So what I want to say that is, in the solution process, we can provide quite different reaction environment just by controlling the temperature, the pressure, by the additives and something like that. So it is very easy for us to control the size, morphology, and something of the products. So this is why we utilize the hydrothermal and silver thermal processes for synthesis of the materials. Here, just to show you the synthesis mechanism during the hydrothermal process. Usually, it is accepted this solution precipitation mechanism was carried out during the hydrothermal and silver thermal process. In the case of the water, because it just has the very high dielectric constant, it has the high solubility in the reaction system. And this will result to the higher saturated concentrations and result to the lower supersaturated degree. So, and at these conditions, instead of the crystal, instead of the nuclear formations, usually the crystal growth will be carried out at first. So as a result, we can get the large particle size. Well, in the case of the ethanol and some other organic solvent as the solvent, because that just has the low dielectric constant, and the result to a low solubility, low saturated concentration, and result to a higher supersaturated degree. And at these conditions, So instead of the crystal growth, more nuclear could be produced and the result to the formation of the nanoparticles. So as a result, we can see this is a case in the oxide. During the hydrothermal utilizes the water as the solvent, we can get the large, comparatively large particles and also agglomerated. And in the case of the ethanol, we can get the more finer particles with the soft agglomeration. Actually, different kind of the solvent could be utilized during the hydrothermal and sulfur-thermal process. Not only the water, but also some alcohols or ethylene glycols could be utilized. Different kind of the glycols process the different lengths of the molecules. Of course, this solvent possesses quite different properties, especially the dielectric constant. The water shows a large dielectric constant, usually in this case, just as mentioned by my last slide. In this case, usually we can get the large particles, while in the case of the organic solvent, we can get the small particles. Here, just to show you the examples of the morphological control of the rare earth oxide by the hydrothermal and sulfur-thermal reactions. In the case of the hydrothermal, we can get the rod-like morphology and the comparatively large particle size, while in the case of the sulfur-thermal reactions, we can get the smaller particles with a spherical-like morphology. And here I just want to introduce an unique sulfur-thermal process, which is developed by our laboratory. We call it the WCISP process. It means the water molecule release sulfur-thermal process. And there are 3 points in the process. At first, no water was utilized as the starting materials. We utilized the solvent consists of the organic solvent such as the ethanol and the acetic acid. Of course, at higher temperatures, the reaction between the two solvents could be carried out to produce the one molecule of the water. This is the first point. And the second point is the following reaction is the hydrolysis. It's the hydrolysis reactions. Such as in the case of the tungsten chloride, it can react with the water, and the water is just come from the first reaction. This is the second point. And also in the addition of the cesium hydroxide, the tungsten reacted with the cesium hydroxide and with the existence of the ethanol, we finally we can get the same cesium tungstenate. And later I will introduce this material also. So this is the second point. And also this process could be utilized for the synthesis of different kind of the materials. Here, just to show you the case of the cesium tungstenate. By the novel hydrothermal process, utilize the water as the reaction solvent. Of course, we can get the single phase of the cesium tungstenate, but we can see the particle size is a little bit large, larger than 500 nanometers. Normally, these materials could be synthesized by the solid reaction process. The higher temperature, more than 1,000 degrees, is necessary. So by the hydrothermal process, we can control the morphology, and also we can get the comparatively small particle size, but it's still larger than the 500 nanometer. So in order to get smaller particles, so we utilize the mentioned WCISP process. As we can see, we can get the single phase, and also we can find the TEM image of the final products, especially in the case of the 10 to 20% of the acetic acid. We can get very homogeneous fine particles, and all the particles just process the same morphology, the homogeneous morphology. And we can see the length is less than 100 nanometers, and the diameter is about 5 to 10 nanometers. And also these products could be dispersed in water and some organic solvents such as the hexane, and it's very easy. And this is also important in the industrial application. And this process can also be utilized for the synthesis of the different materials. Here just to show some simple examples. In the case of the tin oxide, we can get the spherical-like, and in some case we can get the hollow structure. Here just to show you the case of the tungsten-based materials, we can get the quite different morphology, but all of them is just to show the homogeneous particle size. And here just to show you the case of the fibrous titanium. Usually we can synthesize the fibrous titanium by utilize the protonic titanate as the starting materials, just heat it in air. Because of the decomposition of the reaction, we can get the final products of the titanium, but it just has the same morphology of the precursors. In normal case, just by calcination treatment, we can get the fibrous titanium, but the surface is very smooth. Instead of the calcination, we can utilize the hydrothermal or utilize the WCISP process, utilize the ethanol and the acetic acid as a solvent. As we can see here, we can get the very developed structure on the surface of the fibers. And also not only the titanium, but also the nitrogen doped, and also in some cases, the cold doped titanium, we can get the very developed superstructure. And of course, these materials could be utilized for the photocatalyst. Here, just to show you the niobium doped titanium, it is famous materials for the conductive and the infrared light shading materials, and also it can be utilized as the photocatalyst. Similarly, we utilize the ethanol and the acetic acid as a solvent, as we can see by controlling the different solvent. In the case of the 0% acetic acid, 8%, 17, 25, 30, 33, 44, and 50% of the acetic acid. We can control the reactions to get a different amount of the water molecules. In the case of the 50%, because the reaction just produced the largest amount of the water, so the solvent, because of the higher dielectric constant of the water, we can get the large particle size, as mentioned as the previous mechanism. Okay, let me go to the second part, the materials design. I will introduce some detailed examples. The first one is the photocatalyst materials. The photocatalyst material is a very hot topic in the world now. Actually, it was discovered in 1972 by Professor Fujishima. Fujishima was the president of the Tokyo Institute of the Science and also the president of the Chemical Society of Japan for 2 years. Actually, I saw news last week. He and his team just moved to Shanghai Institute of Technology, China, to carry out the photocatalytic research. And as one of the famous photocatalytic materials, the titanium is still very effective because of its low cost and high efficiency for the photocatalytic reactions. And the photocatalysis could be utilized for many areas, such as the purification of the atmosphere and water, self-cleaning, solar cell, and something like that. Here, just to show you the mechanism and the light irradiation, because the titanium is the semiconductor materials. So the electrons and holes could be produced on the conduction band and the valence band. This is the basic principle of the photocatalyst materials. And of course, the electrons and holes could be utilized for the further chemical reactions. Here, just let me show the solar spectra again. As I just mentioned, the solar spectra on the outside of the atmosphere just indicated by the red line, and on the sea level just indicated by the blue line. As we can see, the solar light just consists of about 5% of the UV light, and 45% of the is visible light, and 50% is infrared light. So according to the energy calculation, E equal H mu, we can see the in the case of the titanium, usually it just has a band gap of the 3.0 to 3.2. If we calculate it to the wavelengths, we can get the values of the 378 and 87 nanometers. This means that the normal titanium photocatalytic materials could only utilize under the UV light irradiation. So from here, we can see in order to utilize the visible light effectively, it's necessary to develop the visible light and the infrared light induced photocatalytic materials. There was a famous report on the visible light induced photocatalytic materials. It's published in 2001 in the Science journals. From this paper, they just introduced the anion doping, such as the fluorine, nitrogen, carbon, sulfur, and something. After the doping, the band gap could be narrowed to smaller values. So because the band gap becomes smaller, it can absorb the visible light. It can absorb the light with the wavelength, with a long wavelength light. So and the light irradiation can the semiconductor could be induced to produce the electrons and holes to carry out the following chemical reactions. Until now, different methods has been developed to synthesize the visible light induced photocatalyst materials. The most simple one is the partial oxidation of the nitride, carbide, and sulfide, and something like that. But this process has the disadvantages that at first we should synthesize this nitride, carbide, something. It should be carried out at higher temperatures and need more energies to produce these materials. And also, another example is by the ion injection method is a very effective method to introduce different kinds of ions. But this method should utilize the very big and very expensive instrument to realize the ion injections. So in our laboratories, we are focusing on the hydrothermal synthesis process. So by controlling the different reaction conditions, such as the solvent pH values and additives, we had successfully synthesized the single phase of the brookite, anatase, and rutile of the titanium, and all of them consist of the nitrogen doping, and showed the color of the yellow. And indicated the excellent visible light absorption, visible light induced activities. All of the reaction was carried out in the autoclaver around 200 centigrade. And in the case of the here, just to show you the photocatalytic materials of the nitrogen doped titanium synthesized in solvent, in water, and some organic solvent. And also by utilizing the hydrothermal method, we had successfully synthesized more than 50 kinds of the visible light induced photocatalytic materials, including the nitrogen doping, the carbon doping, the nitrogen and the fluorine co-dope, and some different kind of the co-dope type, the photocatalytic materials. And not only the titanium-based and also the strontium titanate-based materials, we had successfully synthesized the different kind of the visible light-induced photocatalytic materials. And here, just to show you the examples of the characterization for the photocatalytic materials, we utilized the LED lamp as the light source. As we know, this LED lamp is the low energy type, the eco type, the light source. And we utilize the 2.5 watt LED light. And under the light irradiation, such as in the case of the UV type, the LED light, we can get the excellent photocatalytic activity for the denox characterization. And we also changed the different colors of the LED light in the case of the blue, green, and the red. Of course, in the case of the red, it just shows the long wavelength as 627. In principle, this red light shoots a very weak light energy. But even under this red light irradiation, we can get the excellent photocatalytic activity. And also, in order to utilize the solar spectra effectively, we also developed the kind of the photocatalyst which could be working under the infrared light area. Here, just to show you the result of that. We utilized the up conversion phosphor materials. These phosphor materials can transform the infrared light to visible light. Here, just to show you a CCD image of that. In the case of the up conversion materials, it consists of the rare earth, and these materials under the irradiation of the infrared light, it can transform the wavelengths of the 980 nanometers to green visible light areas. Actually, this green light is very weak, but we utilized the weak visible light induced photocatalyst materials to absorb the very weak green light to realize the further photocatalysis reaction. So we combined the carbon-doped titanium with the up conversion materials together. And here we can see in the case of the carbon-doped titanium, of course, it is a very excellent visible light induced photocatalyst materials. And in the case of the up conversion phosphorus, it's not a photocatalyst materials. We combine them together, and under the light irradiation, we can still observe the blue light come from the infrared light. And here, just to show you the photocatalytic characterization result. It's interesting that in the because the in the case of the carbon-doped titanium, it's a very excellent visible light induced photocatalyst materials. It shows the excellent photocatalytic effect and the UV light irradiation and the different kind of the visible light irradiation. But under the infrared light irradiation, with a wavelength of 980 nanometers, we cannot observe the photocatalytic activity at all. Well, in the case of the up conversion materials, because it is not the photocatalyst materials, so and the different kind of the wavelengths light irradiation, no photocatalytic activity could be observed. But if we combine them together, we can find even under the infrared light irradiation, we can get the excellent photocatalytic denox property. And here, just to show you the effect and the UV and the red, green, blue light irradiation, and also and the irradiation of the near infrared light. And this concept could be utilized for different kind of the up conversion materials. We utilize the blue type, red type, and also the green type, the up conversion materials. So we, in all the cases, we can observe the photocatalytic effect. And here, just to show you the mechanism of the process. The up conversion materials usually just shows the large size, and on the outside of the materials, we can coat the narrow size of the carbon-doped materials, which is a very excellent weak visible light induced catalyst. So under the light irradiation, the infrared light could be changed to the blue, green, and red, and the photocatalyst materials at the outside just absorb the blue, green, red light to produce the electrons and holes to carry out the further chemical reaction. And also by the similar concept, we can combine the photocatalyst materials with some different kind of the phosphor materials, such as the long aftergrowth materials. Usually these materials could be utilized as an information board, and in daytime, just under the light irradiation, and in midnight, we can see this could be very effective to utilized as an information board. So we combine these materials such as the nitrogen doped titanium, combined the photocatalyst materials with long after grow materials together. So what result could be expected? So for this composite, not only the daytime, but also in the midtime, we can realize the photocatalytic property. Here, just to show you the different kind of the long after growth phosphor materials. They are different kind of the materials. All of them could be utilized for this system. For not only the daytime, but also midnight, we can realize the photocatalytic property. We call it the full-time active photocatalytic system. So for this long after growth phosphor materials, they can we can realize the different after growth time, and also it also depends on the different wavelengths of the phosphorus. We can utilize the different types of the phosphorus and the different kind of the photocatalyst to realize the full-time active photocatalysis system. This is the case of the strontium-based composite. Under the light irradiation, we can, of course, we can get the excellent photocatalytic activity. But in the case of the photocatalyst materials only. So after turning off the light, we can see the activity will be decreased to about 0. Only in the case of the composite, we can find the catalytic could be kept for a long time, for several hours, even after turning off the light. And here, just to show you the case of the nitrogen-doped anatase type, the titanium combined with different kind of the long after growth phosphor materials, we characterize the acetaldehyde decomposition. We check the produced carbon dioxide concentration. We can find even after turning off the light, the CO2 concentration increment could be observed even after several hours. So from the viewpoint of the to how to design the photocatalyst materials, normally we can utilize the following techniques, such as increase the crystallinity, increase the specific surface areas, increase the light absorptions to decrease the band gap values, or in some case, loading of the noble metals, or utilize the layered compound, utilize the multi-component photocatalysis system. And also a very famous Z-scheme mechanism is also utilized for improving the photocatalytic activity. But from the viewpoint of the synthesis process design, in the case of the high temperature process, of course, it can realize the higher crystallinity, but result to the large particle size and the small specific surface areas, and difficult to get, especially difficult to get some thermodynamically stable, such as the rutile titanium phase with very fine particle size. And also at higher temperature, it will result to the decrement of the doping amount. So by instead of the high temperature process, we utilize the hydrothermal and sulfothermal process. We can realize the fine particles with higher specific surface areas with controllable morphology and fine particles. And also in some cases get the stable phase of the fine particles and realize the co-doping, anion doping, cation doping, and the co-doping to realize the excellent photocatalytic activity. Okay, let me move to the second, to the next topic about the infrared light shedding materials. Okay. Here, just to show you the background of the smart windows, we can see here, just to show you the image of the house, about 71% of the heat exchange is carried out from the window. So if we control the light irradiation for the window materials, we can realize the energy saving in winter and summer. until now, there are different kinds of the materials had already been utilized, such as the metallic film, the lanthan boride, and the very famous ITO and something like that. But there is a problem that is still very limited infrared light shielding properties. And in some cases, the particles just show the large particle size, and it's difficult to get the high transparency of the thin film. So in order to get to improve the properties of the materials, we are focusing on the mixed valence state tungsten-based materials. Just now, I introduced these materials could be introduced by the WCISP process. And by this process, we can control the composition, control the structure, control the morphology, control the particle size. We can see here just to show you the mechanism that usually it is depend on the infrared shielding properties is related to two mechanisms. The one is the plasma effect, and in the case of the you can calculate the plasma frequency by these equations, and it is strongly related to the electron densities. And the electrons just moved between the 6+ and 5+ of the tungsten-based materials, and the polarization and the vibration between the 5+ and 6+ just result to the infrared light shielding. Another mechanism is the effect of the polar, and usually this is related to the particle size. The smaller particle size just shows more, just shows a stronger polar effect, and the result to stronger infrared light shielding properties. Okay, just as I mentioned just now, we utilize the WCISP process to get the very fine particles of the tungsten-based materials, and these materials actually show the very well crystallized fine particles. And also from the XPS, we can find it's just the process to the 5+ and 6+, indicating this composite is the mixed valence state materials. And here, just to show you the infrared light shielding effect, we can see in the case of the tungsten, almost no light absorption within the infrared light area could be observed. While in the case of the mixed valence state, we can get the excellent infrared light shielding in the infrared areas, especially the smaller particles of the products synthesized in the acetic acid. Of the 10 to 20%, we can get the smaller particles and get the excellent properties. And also, in the case of the tungsten suboxide, it also consists of the mixed valence state. And we can synthesize the different particle size by the WCISP process. And also we find the smaller particles just show the better infrared shielding properties. So the smaller particles is very important also. We also synthesize the thin films about the 10 centimeters to 10 centimeters, the comparatively large particles, large areas, and coated on the quartz glass to check the photothermal conversion effect. We can find in the case of the quartz glass, under the light irradiation of the halogen lamp, the temperature inside of the box could be increased to about from the 20 degrees Celsius to 34 degrees Celsius. While in the case of the ITO, the temperature could be decreased to about 30. But in the case of the tungsten session, we can find the temperature could be decreased to about 24 degrees Celsius. So in other words, in summer, if we utilize these materials, we can decrease the time, decrease the temperature increment inside of the room and save the energies. And also, these materials have very unique properties. Under the light irradiation, actually the temperature of the powders and the film increased. And this indicating the mechanism of the light shading might be related to the absorption. While in the case of the ITO, we can see it just shows quite a different behavior. In this case, in the case of the ITO, the light shading is just related to the reflectance of the light. And also, another example is vanadium-based thermochromic materials. And actually, these materials, Dr. Anu carried out many researches on these topics and get very excellent result also. And this material has the semiconductor metal phase transitions at 68 degrees C. The temperature is comparatively higher. So we can utilize these materials coated on the glass. And here just to show you the application image in winter at the low temperatures. This material shows the semiconductor phase, and the infrared light cannot be sheared and pass through the glass. So, so the infrared light can come to the inside of the room to increase the temperature of the room in winter. While in the summer, if the temperature could be decreased to about 30 or 40 degrees C, so the phase transformed to the metallic phase and shows the light shading properties and can shade out the infrared light and can control the temperature increment inside of the room. And this is very important for the application. Of course, the most important point is the critical temperature is still very high. So Dr. Arnaud carried out many works by doping these materials with some anions such as halogen ions to decrease the band gap, to let the phase transformation more easy, to decrease the working temperature of this thermochromic thin film. So here just to show you the synthesis process. It also carried out by the hydrothermal process at at comparatively higher temperature to get the single phase of the vanadium oxide, dioxide. The single phase of the vanadium dioxide is very important. By doping with different kind of the halogen element, we can find the critical temperature decreased to about 48 degrees C. And also here, just to show you some chromic properties of the ion doped materials, we can see the solid line. The difference between the solid line and the dotted line just indicating the thermochromic properties. In most cases, by even after doping the different elements, different halogen element, we can still maintain the excellent thermochromic properties. Okay, because of the limited of the time, I just have the very brief introduction of the next two topics. The first one is the morphological control of the non-oxide-based materials. It is known that by the hydrothermal process, it's comparatively easy for us to control the morphology of the particles, such as in the case of the aluminum oxide for the baymite. We can, by controlling the synthesis conditions, we can get the nest-like or plate-like or different kind of the baymite materials. We utilize the baymite materials with the controllable morphology, utilize these materials as a precursor and followed by the nitridation in ammonia gas. And also we introduced the hydrogen to accelerate the nitrogen reaction process. We can get the different morphologies of the oxide and the oxide, and in some cases the nitride. Here, just the left side shows the oxide, the morphology of oxide. After the nitridation, we can get the morphology controllable of the nitride. And also these materials shows the excellent properties, such as in the case of the SPS sintering. The plate light just shows excellent sintering properties. It can be sintered completely at a completely lower temperature compared with that of the needle-like morphologies. Here, just the right side just to show you is the gas sensing properties. Of course, in the case of the gallium oxide, it also shows the excellent sensing properties. But compared with the oxide, we can find the nitride shows the more higher sensing properties. And also here just to show you the measurement equipment and the mechanism. Because of the limitation of the time, I just just go to the next part. We also focused on the two-dimension materials. In the case of the MOS, the metal oxide materials, semiconductor sensor materials, of course, it has many advantages, such as excellent high temperature sensitivity, the very wide the measurement range, and excellent response and something like that. But it showed a very high working temperature and poor selectivity. So in order to get the higher properties, we are focusing on the two-dimensional materials. And of course, the most famous two-dimensional material is the graphene. It has the excellent properties and has many applications. But these graphene materials, if we utilize it for the gas sensing detections, it has a very limited disadvantages because the small band gap, because of its small band gap and the lack of the semiconductivity and the very limited switching characteristics. So we are focusing on the room temperature gas sensing applications. We utilize two different kinds of two-dimensional materials. So one is molybdenum sulfide-based materials, and another is MaxIn carbonate-based layered compound. This material shows very large specific surface areas, and more importantly, we can control the more edges, more active sites on the surface, and realize the excellent properties of the gas sensing. I have almost no time, so just to show you the very brief result of that. We can here just to show you the case of the molybdenum sulfide, and here this is application for the monitoring for the breathing and skin monitoring. We can monitor the gas, the deep breath, normal breath, and the fast breath, very sensitive. And also this two-dimensional materials shows very excellent selectivity and of course, the stability and the reproducibility, and it can be utilized for a long time, for stable utilized for a long time. And in some case, we can utilize the selenide as a different element for the replacement to the sulfide to realize the higher selectivity. Here, this result also selected as the cover image for the applied nano materials. And here, just to show you the result of the MaxIn-based materials, because of the limitation, I just give you the result about the sensitivity, resistance, and the response measurement result of the MaxIn-based materials. So from this, we can get the conclusions that it is the two-dimensional materials also has the great potential for the room temperature gas sensing and shows the very wide applications. So this is the last slide of mine. I just want to summarize my talk by utilizing the eco materials concept. We utilize the we synthesize the eco materials by the eco process. To introduce here, just to introduce some examples of the synthesis, the processing method, and considered about the friendship to human and the environment, aiming for the advanced environment-related applications. So in order to realize the sustainable development, the fabrication of the eco materials by the eco process are expected to greatly contribute to the modern human society. Okay, thank you very much for your attention. Here just shows the photographs of the Dr. Anu, and he got the PhD in my group, and another two Indonesian students. All of them are very active in my and very active in my group. Thank you very much for the students also and the staffs and also the Indonesian students for the support for my research. Thank you very much.
Okay, thank you so much, Professor Suyin. This is a very interesting presentation, and I think it's also very awesome materials. So give applause for Professor Suyin.
Thank you very much.
Okay. So I just got information that do you have any activity after this, or you will you can continue or you have another activity?
I'm so sorry. This morning, I just sent the mail to Dr. Anu. I have another 2 meetings this afternoon. Maybe I can join the next talk, but after that, I should leave your meeting.
Okay. if that's so, we thinking that maybe if you have another activity, another place, so that means we will give opportunity to audience, to participant to give you some questions right now.
Okay, no problem.
Okay.
Yeah.
Okay. Thank you. So please,
Thank you very much.
maybe all participants want to ask a question for Professor Suyin. So
yeah.
You can raise your hand, or maybe you can write on the chat room, something like that. So you can asking to Professor Suyin right now. Please, maybe 10 to 15 minutes, something like that. Okay, maybe. Okay, Professor Suyin, this is there is one question.
Yeah.
Okay. Hello, Professor Suyin. I am Michael from General Sudirman University. I want to ask you questions about your presentation according to your research so far. We know some materials that can use for photocatalytic, like titanium dioxide or maybe silver phosphate and others. My question is, what is the best photocatalytic materials right now then that can we synthesize by sulfur-thermal reactions? Which material the best material for sulfur-thermal reactions? And then we know until now pandemic is still happening. I want to know how can inorganic material can be useful in pandemic. Thank you so much. Maybe there is two questions, Sensei. First is what is the best material for sulfur-thermal?
Okay, thank you very much.
Yes.
And actually, there are different kind of materials that was developed for the photocatalysis applications. In principle, if it is semiconductor materials, they should have the photocatalytic properties. But until now, the titanium is still the most effective photocatalytic materials. Many researchers are still focused on this one by doping different elements or by changing the phase, something like that. And also the silver phosphate is also a famous materials and photocatalytic materials. Professor Slimer also focused on these research topics and published many papers about that. And in the case of the silver phosphate materials, it's important to control to get the fine particles. It is a little bit difficult because even at low temperatures, the large particles could be produced. So many process has been developed by Professor Smile also to synthesize the smaller particles and control the morphologies to get the more higher photocatalytic properties. And actually in Tokyo University, there is a famous group on the photocatalytic materials, the domain synthesis group. In his group, he also developed different kinds of materials, especially the composite, the titanium and the niobium contained materials, which shows very higher photocatalytic activities. Even under the irradiation of the solar light, the water can be decomposed to water, to hydrogen and oxygen directly. And now there also has a big project to research how to improve the efficiency more and more. They coated the materials on the glass in order to get more hydrogen just under the irradiation of the solar light. Actually, in Japan, there are many groups still focus on the different kind of the photocatalytic materials. I think it still has many topics and many materials that we should develop. Thank you.
Okay, how about in your experience? What kind of material from your experience, your own experience?
And in my group, and of course, the titanium and the silver phosphate, of course, they are important and should have very high photocatalytic activity. And in my group, I still researched on the different kind of the ion doping. And not only the cations, but also the anions doping of the titanium materials.
Okay, thank you so much, Professor. How about the second question is, maybe it is possible to do kind of application for pandemic, especially for COVID-19 pandemic, for your, I mean, your method?
In principle, the under the light irradiation, of course, the photocatalyst has the effect to decompose, to attach attack the wheels. Because there is advantage for the photocatalyst materials, that is the reaction just produces the electrons and holes. The electron and holes attack the organic compound. Almost no selectivity of these materials. They attack any one of the materials. So in this viewpoint, it should be very useful to attack the wheels, to decrease the corona wheels by under the light irradiation. Actually, recently some research also focused on this topic.
Okay, thank you so much. And then the second question is from Asep. When do we as researchers determine a chemical compound and can produce suitable energy for a photocatalytic? Number one, Sensei.
Number one.
Yes. Number one question. Yes.
Chemical compound can produce suitable energy for us.
Yeah.
Yes. As I mentioned just now, the Tokyo University group had researched some materials which can decompose the water to hydrogen and oxygen directly. This one should be suitable for the energy topic, I think.
Okay, thank you so much. Very interesting. Very, very interesting. Okay, maybe there is one more question. Maybe we still have 5 minutes. Maybe someone want to ask directly. It's okay. You can raise your hand, or maybe you can write the question, please. How about Mr. Anung? Mr. Anung, maybe is one of your favorite student, maybe, Sensei. Yes, Mr. Anung, maybe you have one question, maybe. We still have maybe 3 or 4 minutes. Okay. Okay, maybe if there is no.
Dian, please ask the question.
Okay, please. Please, if you want to ask question. No? It is okay or no?
In the chat.
Okay, please. Please tell your name from affiliation. No? Okay. If there is no question, I just want to one question, maybe. Last question, maybe, okay. Professor. This is it is possible to widen the band gap of graphene. It is possible to widen the band gap.
Actually, in my research group, I didn't do the related work to control the band gap of the graphene. But another group in our institute, famous professor Nishihara Sensei, he just does many researches on the carbon-based materials. And he told me it's possible to adjust the band gap of the graphene also. In his group, he had successfully synthesized the graphene materials with the conductor properties or with the semiconductor properties. And this is very interesting for the gas sink application also. And actually, I also had the collaboration with his group and asked another Indonesian student, Mr. Taufik, to do some gas sink characterization for these materials. Unfortunately, until now, we cannot get the more positive result about the graphene-based materials. In this case, only shows very low gas sensing properties. Maybe in the future, we can, after detailed control of the structures, maybe I hope we can get some positive result about that.
Okay, so in theory, it's possible, right, Sensei? It is possible. Okay. Yeah, maybe possible. There is more 2 questions, Sensei, because okay, I will read one. It's from Dian Windy, number 3. Can anion and cation be added together simultaneous to narrow the band gap of photocatalysis material?
Sure, it's a very nice questions. Actually, we had carried out some related experiment. In the case of the cation anion doping, usually the anions just come to the positions of the oxygen side, such as in the case of the nitrogen, it just shows the -3 valence state, and they come to the oxygen, which is the -2. So if you introduce the one nitrogen to the oxygen side, in other words, you will introduce the oxygen vacancies again. If you introduce the cations and anions together, we can avoid this problem, such as in the case of the niobium and the nitrogen, we can realize the co-dop by the hydrothermal process. And in this case, of course, because these materials show less crystal defect and show the higher photocatalytic activity. Thank you very much.
Okay, thank you so much, Professor Suyin. There is still some questions, Sensei.
Yeah.
But maybe time is not so much. So maybe I will read the last.
Yeah.
Okay, I will read the last question. Maybe another question, maybe we can asking later. Okay, number 4.
Yeah.
My name is Habibullah from General University. My question is, how important is the aging treatment in the synthesis of nanomaterials?
Okay. Okay, it's a very nice questions. And in my case, almost no post-treatment, no aging process was carried out because the hydrothermal and the superthermal process, there is advantages that we can get the well crystalline particles, but still with very small particles. In most cases, we don't utilize the post-treatment. We don't utilize the aging process. And of course, in some case, if you introduce the aging process, treatment, you can more decrease the crystal defects on the surface or something that, and increase the properties, of course. But in our case, almost no post-treatment was carried out. I don't know if this is the answer. This answer is okay or not.
Okay. Thank you so much. Thank you so much, Sensei. I think because of time, we still have some question, but maybe we can ask it later. Maybe we can discuss by email or something like that.
Sure.
So thank you so much for your very interesting presentation.
Thank you very much for your very nice conference. I'm sorry, after this this afternoon I cannot join the discussion.
Okay. Yes, maybe
thank you very much.
As we know that now in Japan, different 2 hours, right? 2 hours with us, Indonesia. So that means now is already afternoon. In Indonesia, still morning, but in Japan,
now it's time to deliver.
Yes. Yes. So thank you so much, Sensei.
Thank you very much.
Thank you very much, Sensei.
Okay, thank you so much. Okay, and then now maybe can prepare the committee. Maybe committee want to give Professor Suyin kind of certificate. You can show us. How about the certificate, please? Okay, thank you so much.
Now it's time to deliver a certificate.
This is the
for Professor Suyin.
Thank you very much. And I hope we will meet together in the next maybe volume, and then also hope you will be more successful in the next future. And then thank you so much. Arigatou gozaimashita.
Thank you very much.
Okay, thank you so much for committee. And then now we are continue for the second speaker. The second speaker is the second speaker is the Associate Professor Dadan Hermawan. Okay, Dadan Hermawan, and then I will let me read a brief profile for Associate Professor Dadan Hermawan. Okay. Mr. Dadan Hermawan is from Jenderal Sudirman University, and then he got the bachelor degree in chemistry from Pajajaran University, Indonesia, master degree in chemistry also from Bandung Institute of Technology, Indonesia, and then got the PhD degree in chemistry from University Technology Malaysia, UTM, Malaysia. His research interest is area of analytical chemistry, especially in development of high-performance liquid chromatography, capillary electrophoresis methods for the chiral and non-chiral analysis of the selected pesticide and drugs. There is so many publications from Mr. Dadan Hermawan. Maybe some of the publication in Applied Surface Science Journal, and then also Serality Journal, and also Journal of Exploration Science. There is so many, so maybe I will not read one by one. And then how about the honor and awards? So Mr. Dadan Hermawan also have so many honor and awards, like maybe one is a silver medal award researcher in Malaysia Technology Expo MTE 2011, also silver medal from the second 12th Industrial Art and Technology Exhibition in ATEX 2010, and another honor and awards. And also Mr. Dan Hermawan have 5 patents, already have 5 patents. And then also the current research project is world-class research by the RPM Dikti. And then actually I know him very much because he is my colleague at the same department, at the same university. And maybe one of information that he is one of the rising star of the researcher in our university. Yes, he is one of the rising star in our university for the research in our university. And then Jenderal Sudirman University. So to shorten the time, Associate Professor Dadan Hermawan will present his research entitled Application of Capillary Electrophoresis and High Performance Liquid Chromatography Methods for Enantiospiration of Selected chiral compounds. So, Associate Professor Dadan Hermawan, now time is yours.
Okay, thank you very much, Dr. Roy Andreas, for the very nice introduction. Thank you, Dr. Roy. Also, I would like to thank to all of the committee, especially Dr. Anung Panitra, who inviting me to join as a plenary speaker in this JCC 2021, and also for all participants who join this conference. Thank you very much. And then I would like to share a little bit of our research and publication maybe on the application of capillary electrophoresis or CE and high performance liquid chromatography or HPLC is the popular methods in the analytical chemistry for the non-expression or the non-numeric expression of selected chiral compounds. Okay, we continue to the this our partner in the international collaboration. Firstly, Professor Dr. Hassan Y. Abdul Inain from the National Research Center Egypt, and then our supervisor in UTM, Professor Dr. Wan Ibrahim, and Professor Muhammad Marsin Sanage from University Technology Malaysia. So some of the result of this presentation is come out from our research collaboration with them. Okay, ladies and gentlemen, this is my outline for this presentation, introduction, and then application of CE, and also application of HPLC, and the last about the research in progress in my group, and acknowledgement. Firstly, this introduction about the importance of non-numeric expression, or we call the non-expression. Firstly, non-theomers or chirality is vitally important in chemical, pharmaceutical, and also agricultural industries. And then produce critically different pharmacological effects in biological system. And then to evaluate the non-numeric purity of chiral compounds or analytical determination. So the isolation of pure enantiomer is also important for the enantiomer separation. Maybe we remember about the Thalidomide Scandal in the late of 1950s and early 1960s. The use of thalidomide in about 46 countries by women who were pregnant or who subsequently, become pregnant, resulted in the biggest man-made medical disaster ever, resulting in more than 10,000 children born with a range of severe deformities such as pocomelia, as well as thousands of miscarriages. The male formation due to maternal ingestion of thalidomide. So we can see this the birth defect because the her or his mother is consume the thalidomide drugs for the morning sickness effect. Yes, this is the structure of the thalidomide, the morning sickness drug that causes birth defect. This is the S thalidomide, and this one is the R thalidomide. It has one chiral center, so it has a pair of enantiomers. R thalidomide, the green one, is the effective agent against morning sickness, but the S thalidomide is teratogenic and cause birth defects. So we need to separate this enantiomer before the drug is distributed to the consumer. So we let about the information about the enantiomers. What is the enantiomers? Enantiomer is the two non-superimposable structures that are mirror image of other. Same with our hands. Yes, this the non-superimposable structure that are mirror image of each other. Enantiomer is identical in physical properties, but or except for the direction in which they rotate the plane of polarized light. And also enantiomer is identical in chemical properties, but or I said except in their reactivity toward optically active region. So there's different pair of enantiomers in the direction in which they rotate the plane of polarized light, and plus or minus. Okay, and then in the reactivity toward optically active region or the chiral selector. So the biological activity of each enantiomer is different from each other. For example, the thalidomide, R and S thalidomide. And suppression of enantiomer is required for the determination of quantity of each enantiomer, and also for the isolate the pure enantiomer of the drugs. This capillary electrophoresis system. CE is one of the expression methods suitable for routine application. And then this one, the advantages of CE method, high efficiency, and also fast analysis, less than 5 or 10 minutes. Also inexpensive because for the running CE only using the buffer, and then use minimal organic solvent, and also minimal waste generated. This is called environmentally friendly or green chemistry. So this is our focus on this research. We develop method with the green chemistry or environmentally friendly. So this the wide application of the CE, for example, for agrochemicals. In our research, we apply CE to the chiral expression of the triazole fungicides. Yeah. The big three of the pesticides, I think, after the insecticide and also herbicides. So the fungicide is the big three, and also pharmaceuticals. Many drugs, maybe about the antifungal drugs, anti-inflammatory drugs, and so on. They can be analyzed by the CE, and also cosmetics. Sorry. Food industry, health and medical, forensic also, and then yeah, okay. This is the wide application range of the CE method. This is the CE instrument of the capillary electrophoresis basic equipment. It's the simple basic equipment, two electrode, anode, the positive, and the cathode is negative electrode. the detector, and then the capillary tube, and also power supply, and then the two buffer reservoir, source reservoir, and then destination reservoir. Okay, let's move to the maybe more detailed the illustration of the CE system. Maybe for our student, we until now we have not found the CE instrument in the our university or maybe in the Indonesia, because maybe the limitation of the CE. Yeah? So this the two buffer reservoirs in the CE, very small, the capillary column about the 50 micrometer and then 100 micrometer, and this the electrical isolation using the platinum electrode, high voltage supply up to 30,000 volt or 30 kilovolt, and this using the detector. And then this is the information about the sample injection or introduction. The firstly using the gravity injection, something like that. Yeah. The sample injection using the gravity, different in height, causes sample to flow into capillary. This is the capillary. Then the buffer is replaced and voltage applied. The high voltage supply. This is the inlet buffer and this is the outlet buffer. And the second one is the pressure injection. Using the pressure, the sample introduced from the inlet buffer using the pressure, and then the sample will move to the outlet buffer, and then will be detected using the second one, the pressure injection using the vacuum. Yes, the vacuum in the outlet, and then this the buffer, and then and it will follow the flow, the mobile phase. The electronic injection, the third one, and then using the electronic injection, then the buffer is replaced and voltage. All of this injection technique control injected sample volume by choosing an appropriate receivable time of sample introduction with the pressure or sampling voltage applied. Typical sample volume are the nanoliter, 1 to 10 nanoliter for the normal CE, but we can optimize the volume. So the electroosmotic flow, unlike PLC, there is no pump in CE. Unlike GC, there is no pressurized gas flow in CE, and unlike paper chromatography, there is no capillary action. The case buffer, we use the buffer for the mobile phase. Is the electroosmotic flow or EOF. Yeah. It's a schematic representation of the fused silica capillary tube. Yeah. And sorry, the buffer solution has equal amount of cation and anion. The double layer of the capillary inside. The immobile solenoid anion pair with a mobile buffer cation forming the double layer along the wall. The remaining buffer cation is the double layer are attracted to the negative charge of the cathode. It's the electroosmotic flow or EOF. Yeah, dragging the bulk buffer solution with gum. And also buffer injected analysis, the third flow from the buffer to contain the anode toward the reservoir containing the cathode from inlet to outlet buffer. If the capillary wall is treated with a cationic surfactant or one is added to the buffer, the wall will be positively charged and the electrolytic flow will be reserved. That is toward the anode. And then continue to the sample size and column length in CE. Because the small diameter of the CE capillary, 25 to 100 micrometers, CE sample are some of the smallest of any modern chromatographic method. So for example, for HPLC, routinely 10 or 20 microliter, GC about 1 microliter, but in CE only 1 nanoliter. And then the motive force that drives it of the analysis in CE is a function of its analytic ionic charge, the ion mobility in the buffer, and the electrical potential across the capillary. It is the unlike GC, longer column mean more specific. In DC, longer capillary doesn't increase the number of vertical plates or N in chromatographic term. Detection in CE, like HPLC, we use the UV absorption and also using the other, for example, using the C4D detector, and also we can also using the combination with the MS, LCMS. Yeah, this compress its polyimide coating remote. So we burn the polyimide, and then we get the clear of the silica. Yeah. Then with the coating remote, sort light can send a tau. Then to increase the absorbance, sending source light through a longer path length and can be achieved by different configuration. So the development of the detection in C is also the one of the topic in the CE method. And then electropherogram, like a chromatogram in HPLC, so is a plot the time from injection to x-axis and also detector signal in y-axis. In the example below, indirect detection in values. And this one, the time, we call the migration time. Yeah. And this one, the absorbance. So many information about this implementation of the CE. Yes. About the better of CE compared to gel electrophoresis. Yes. And then small sample size important. Okay. See, sample volume can be spectacularly small using modern CE autism. But we can also maybe in last week can explain about the online reconstruction of the CE method to increase the sensitivity of the CE method. Okay, we continue to the MEKC. What is the MEKC? MEKC or micellar electrolytic chromatography is this method is introduced by Prof. Terabe from Japan in 1984. MEKC is a hybrid technique combining electrophoresis and chromatography. MEKC is a powerful technique to solve many chemical analysis problems using CE instrument without any alteration. And then it was developed into a powerful expression technique for enantiomers. Many papers published for the enantiomer expression using the MEKC method. There are two modes of enantiomer expression in MEKC. The first one is using a chiral surfactant. So MEKC using chiral surfactant, we call the chiral MEKC. And the second one is the MEKC using a chiral surfactant in combination with cyclodextrin or CD as chiral selector. Name is the cyclodextrin modified MEKC or CD MEKC. This one, the schematic illustration of MEKC expression. The principle of expression in MEKC is based on the solid partitioning between the micellar phase and the aqueous or solution phase. The technique provides a way to resolve neutral molecule as well as charged molecule by CE, different with the conventional electrophoresis. Yes, the component will be separated due to the distribution equilibrium between the micellar phase and the aqueous phase, both of which move at different velocities. Surfactants are added to the buffer solution above its CMC, critical micelle concentration. So we dissolve the surfactant above the CMC value. Micellar solution may solubilize hydrophobic compound which otherwise would be insoluble in water. And this one, the illustration of the CD-MEKC expression principle. In the CD-MEKC expression mode, the migration behavior of the individual enantiomer is determined by their competitive equilibrium between the aqueous phase, and then the micelle, and also the CD or cyclodextrin. The addition of the CD to the buffer displays the distribution of the analyte from the micellar to the aqueous phase due to the interaction between the water-soluble CD and the analytes. This is the illustration of the CD-MEKC expression principle for the enantiomer expression. Okay, ladies and gentlemen, let's move to the application of the CD-MEKC for the chiral expression of the triazole fungicide. What is the triazole fungicide? Triazole fungicide is the one of the most important categories of fungicide. It has excellent protective, curative, and also eradication power against a wide spectrum of crop disease. And then the chirality is expected to play a crucial role in bioactivities of triazole fungicide. This is for example, the selective triazole fungicide, the famous triazole fungicide. For example, fenbuconazole, it has one chiral center. Tebuconazole, it has also one chiral center. And then the propiconazole, it has two chiral center. So this is the chemical structure of the propiconazole enantiomer. It has two chiral centers, so it has two pairs of enantiomers. of 4 stereoisomers or isomer optics. Yes. This one the 2R and 4S propiconazole. This one the 2S and 4R propiconazole. And this one the 2R and 4R propiconazole. The last one is 2S and 4S propiconazole. We have developed to separate this 4 individual enantiomers. So this is the previous study from other researcher about the propiconazole separation using the HPLC chiral column 1201 by Regis Technology. This result, only 3 peak of propiconazole is observed using the mobile phase, the isopropyl alcohol, hexane, and acetic acid, and the 1 ml per minute flow rate, 254 nanometer UV absorbance, and runtime about the 70 minutes. So this maybe too long. Yes, yes. This one the result from a previous study about preponderant enantiomer expression using the HPLC, and then this also the result from other researcher about the chiral separation of the propiconazole using the CDMEKC. The penmetsai used the CDMEKC for enantiomer and isomeric separation of 7 pesticides, including the propiconazole, but only 2 isomers of propiconazole peak were observed. 2 peaks from 4 peaks, so it's not fully complete separation. They use the condition with the 50 micrometer ID capillary column, 47 cm long to detector, yes, 40 cm to detector, and then capillary column is the Fraser injection 2 seconds or equal about to 2 nanoliter, 50 millimolar sodium hydrogen phosphate plus 50 millimolar SDS sodium hydrogen sulfate as the surfactant, chiral surfactant, and then 15 millimolar dimethyl beta cyclization as the chiral selector. pH 7 20 kilovolt. This generate the 67 microampere, 214 nanometer UV absorbance. It has only 2 peaks of enantiomer. So we use this background about the optimization of MKC method for chiral expression of propiconazole. Firstly, we try to optimize the MKC with biosalt as chiral surfactant. So we call the chiral MKC, but however, we only get 2 propiconazole peaks. Data not shown in this presentation. We have tried about maybe 6 months about this optimized method, but there is no result about the 4 peak of propiconazole. And then we continue to the CDMEKC with HP gamma CD as chiral selector. SP gamma acid is the derivative of CD, and then we got the 4 peak of propiconazole, and then we also developed the online sample preparation technique, namely the stacking and sweeping method for the enhance the sensitivity of the method. This one the flowchart of the optimization, also the sweeping CDMKC at acidic condition, pH 3, we get the simultaneous chiral expression of 3 triazole fungicide, propiconazole, tebuconazole, and also penbuconazole in 1 injection, the simultaneous separation. And then we also developed the SPE sweeping CDMKC for the determination of the triazole fungicide in grape sample. So this is the result. Sorry, this is the maybe the information about the stacking. What is the stacking? In MKC, sample stacking is defined as the movement of ion across a boundary that spares a region of low and high electric fields. Stacking is obtained when the conductivity of the sample is significantly lower than that of the running buffer. Sample stacking fluid is normal mode MKC condition where UF is strong and analytes are brought by the UF is the normal stacking mode. So the sample is prepared by dissolving the neutral analytes in a low conductivity solution. So we use the water for the solvent. Long plug of low conductivity solution containing the sample is injected into the capillary purposely filled with a high conductivity suppression or background insulation. So this is the sweeping. The other technique for the online preconcentration in MKC. Sweeping in MKC is defined as the picking and accumulating of analytes by the procedures replace or micelle that fill or penetrate the sample zone during application of voltage. The fundamental condition for sweeping is a sample matrix free of the micelle used, and the sample matrix has similar conductivity with the running buffer. Picking and accumulating of the analyte occurs due to partitioning or interaction of analytes with micelle. Therefore, sweeping preconcentrate due to a partitioning mechanism. So, ladies and gentlemen, this one the result from the optimization of the non-aspiration of propiconazole by CD-MKC method using the HP gamma CD as chiral selector. 4 stereoisomers peak were observed and well separated. The baseline aspiration, the RS higher than 1.5. This non-aspiration of propiconazole by the CD-MKC method, the solution solution using the 30 millimolar HP gamma CD. So previously we optimize the concentration of the CD using the HP gamma CD for the 10 millimolar, 20, 30, and 40. So we get the optimized CD as the 30 millimolar. And then 50 millimolar SDS, sodium dodecyl sulfate, is the achiral surfactant. So we also optimize this concentration of the SDS from lower to higher. And then also we use the organic modifier, for example, methanol and acetonitrile, to increase the resolution of the non-theomeric aspiration of the propiconazole using the combination 10% of methanol and 5% of acetonitrile in 25 millimolar phosphate buffer pH 7. Sample propiconazole standard 200 milligram per liter of ppm. In methanol, applied voltage 30 kilovolt is the optimum applied voltage and temperature 20 degrees Celsius. So this is the electroprogram of propiconazole enantiomer, the optimized CD-MKC and online CD-MKC under neutral condition. The electroprogram A is the CD-MKC, the normal CD-MKC, sample injection 1 second at 50 millibar. This using the pressurized injection. And the B electroprogram is the normal stacking mode CD-MKC using the 20 milligram per liter propiconazole. So lower than the CD-MKC, the normal. Sample injection 15 second at 50 millibar. So we use the more injection time for the sample injection. The last one, the C is the sweeping CD-MKC using the 10 milligram per liter propiconazole, sample injection 90 second at 50 millibar. And then the aspiration solution using the 30 millimolar HP gamma CD, 50 millimolar SDS, methanol acetonitrile 10%, and 5% volume to volume per volume in 25 millimolar phosphate buffer pH 7. And the length of capillary, we use the 64.5 cm. The effective length is the 56 cm to the detector. Applied voltage 30 kilovolt, detection wavelength 200 nanometer UV wavelength, and then the temperature 20 degrees Celsius. We have the all peak of propiconazole is resolved. That is the analytical performance of the CD-MKC and SM CD-MKC and also sweeping CD-MKC. The linearity rank CD-MKC from 50 to 200 ppm, and SM CD-MKC from 2.5 to 20 ppm, and sweeping from 1 to 20 ppm propiconazole. The R square or coefficient determination higher than 0.999 for all the method. And then the RSD or repeatability of the migration time, peak area and peak height also quite good. And then the LOD of the CD-MKC about 10 ppm and SM CD-MKC about 2 ppm, and then sweeping is 0.4 the ppm of the LOD. And then we have the SEF, sensitivity enhancement factor. This is the equation LOD of CD-MKC per LOD online CD-MKC. So we get the improvement of the sensitivity enhancement factor 5 times for NSM, and there 25 times for the sweeping CDMK. This is the online preparation of the sample. Okay, and then we continue to the electroprogram of the selected chiral triazole fungicide by CDMK at acidic pH. Under acidic pH, pH 3. So this one, the electroprogram is the 50 milligram per liter or ppm fenbuconazole, tebuconazole, and also propiconazole. So we inject the mix of the triazole fungicide in one injection. We can separate the 8 peaks, yeah, 2 peaks from fenbuconazole, 2 peaks from tebuconazole, and then 4 peaks from propiconazole. So this one, the B is the 1 ppm fenbuconazole, tebuconazole, and also propiconazole, sample in buffer solution without micellar phase, yeah, and then injected for 120 seconds at 50 millibar, present voltage minus 25 kilovolt, because we use the acidic pH, so the voltage the negative 25, and other condition is in the CDMKC pH 7. This is the analytical performance of the result, linearity, repeatability, SEF, and LOT of the optimized sweeping CDMKC method under acidic condition. For the fenbuconazole, yeah, this one the result, yeah, and then tebuconazole, the R square higher than 0.9, and then the RSD also less than 2%. SEF is the fenbuconazole for 30 and tebuconazole 70, and the propiconazole 100. So this one the result for each peak of the enantiomer of the triazole fungicide. And then this one the electroprogram of the enantiomer expression of the triazole fungicide spike in grape sample. After we confirmation that the grape sample there is no analyte, yeah, so we spike the grape sample with the standard as and then we continue the SPE for the preconcentration and also clean up of the sample, not unknown peaks from the sample matrix. This one the 2 peak from fenbuconazole, 2 peak from tebuconazole, and then 4 peak from propiconazole. This one the result, yeah, percent recovery and repeatability of triazole fungicide spike in grape sample by SPE sweeping CDMK. So we combine the offline technique, yes, the solid phase extraction for the preconcentration of the analyte and also clean up, and sweeping the online preconcentration in MKC and CDMKC, EH3. And then this one, the MRL, minimum residual limit established by the CAC, Codex Alimentarius Commission. So the appraised recovery about the fenbuconazole about 109, tebuconazole 73, and propiconazole 74. So the RSD, this MRL. Okay, this one the concluding remark for the chiral expression of the triazole fungicide. This is the MKC method for the expression of 2 enantiomer pairs of was successfully developed. And then the result showed that MKC method provide high expression efficiency for the expression of the propiconazole enantiomers. Good repeatability in the migration time, peak area, and peak high were obtained ranging from 0.2 to 5.7%. And then calibration curve are linear with the correlation coefficient higher than 0.99. And then online comparison and chiral expression of selected triazole fungicide using CDMKC was successfully developed. And also the optimized sweeping CDMKC at pH 3 gave the best detection sensitivity and was successfully applied to the simultaneous expression of fenbuconazole, tebuconazole, and propiconazole in only one injection. And then the LOD for the 3 selected triazole fungicide range from 0.09 to 0.1 milligram per liter, well below the limit set by CAC. The result provide lower LOD for the triazole fungicide compared to the previous study on the enantiomer expression using the HPLC. This one the certificate of grant of patent during my postdoc in UTM. This one the another result, expression of 3 other triazole fungicide by CDMKC. The simultaneous expression of the tebuconazole, hexaconazole, other triazole fungicide, and fenbuconazole. So this one the other result and also publication on the cyclization modified efficacy for non-transference of other compounds, yes, hexaconazole, penconazole, and myclobutanyl. 6 peaks were observed and well separated in one injection. Yeah, the hexaconazole, penconazole, and myclobutanyl. So we get the 6 peaks using the optimized CDMKC method. In this one, the stacking and sweeping in CDMKC for chiral expression hexaconazole, penconazole, and meclobutanil. This the using the stacking and sweeping. We get the optimized method for the CDMKC using stacking and sweeping. And the last one is the chiral expression of ciproconazole, bromoconazole, and diniconazole, other triazole fungicide using the CDMKC. We get the 10 peaks, were observed and well spreaded in only one injection. Diniconazole, it has 2 peaks, and then bromoconazole, it has 2 peaks, and the last one, ciproconazole, also have 4 peaks from the 2 chiral center of the analyte. And this is the certificate of grant of the patent in UTM Malaysia. Okay, we continue to the chiral expression of azole drug using CDMKC. The azole drug are widely used for the treatment of topical fungal infection in a variety of pharmaceutical formulation. Antifungal activity of this agent is due to the presence of an aromatic heterocyclic, an imidazole or a triazole. Previously, there is only one report concerning the chiral expression of azole drug, namely miconazole by CDMKC using the dual system CD. So they use the dual CD system. So we have developed the CDMKC method for the chiral expression of iconazole and also sulconazole. So we published in the Journal of Pharmaceutical and Biomedical Analysis for the iconazole or the sulconazole in preparation. We will compare with the HPLC method. And also this one, the electroprogram non-expression of the selected imidazole drugs at optimum CDMKC condition using the expression condition 35 millimolar Hb gamma CD, 10 millimolar dimethyl beta CD, 35 millimolar phosphate buffer pH7, 50 millimolar SDS, 15% volume per volume acetonitrile, and using the applied voltage 27 kilovolt, and also using the expression temperature of 30 degrees Celsius. Analyte injected electrokinetically, not pressurized, but using the applied voltage, using the voltage. 3 kilovolt for 3 seconds. This one is the RS thioconazole, 2 is the RNS isoconazole, and this one the fenticonazole. It has the 1 chiral center. And the last one is the chiral expression of fenfosetin using CDMKC is different class of the drug. This fenfosetin is a synthetic derivative of the vinca alkaloid kinsamine. It has 2 chiral centers, so you get the 4 peaks of individual nantiomers. So this the 2 pairs of nantiomers. This 1 pair, and this one is the 1 pair. There is program of nantiomer expression of fenfosetin using this CDMKC with 40 millimolar Hb beta CD, another derivative of CD, in 50 millimolar phosphate buffer pH7 containing a 40 millimolar SDS as a chiral surfactant, and expression voltage 25 kilovolt, expression temperature 25 degrees Celsius, and electrokinetic injection at 5 kilovolt for 5 seconds. The chiral recognition mechanism of this expression, the electrostatic interaction, hydrophobic interaction, and also hydrogen bonding interaction between selected chiral triazole fungicide and also azole drugs, and cyclodextrin play a critical role in this chiral recognition mechanism. And also, Prof. Scriba also mentioned the formation of transient diastromeric complex between chiral analyte and chiral selector by hydrogen and halogen bonds, ionic dipole-dipole, and also van der Waals are the basis for chiral expression. This one, the chiral recognition mechanism. Okay, because the limitation of the time, we continue to the HPLC method for chiral expression. This the current research with our collaboration with the Prof. Mudasir in Gajah Mada University. We have 3 methods about the HPLC method for the chiral expression. It's the famous method. The first one, the chiral derivation reagent or CDR. The advantages of the method is the less expensive, flexible, different selectivities, and also what the non-expensive, yes. But the disadvantage of this method is the long analysis time, inconvenience, need to synthesize non-commercially available pure debating reagent. The disadvantage of the chiral debating or CDR. Yeah. And the second one is the chiral surface or CSP. Large number of commercially available chiral column, convenient or also simple operation, easy the operation, but the expensive of the chiral column. Yeah, difficult to select the CSP for the special or the different enantiomers. Can only spare very few kind of enantiomers. And then the last one is the chiral mobile phase additive or CMPA. The advantage of this method is less expensive LC column. We can use the conventional LC column, for example, the C8 or C18. Wide variety of additives, different selectivities can be obtained. But the disadvantages is the mode operation is complex and also inconvenient for preparative application. So we select this method is chiral surface for the current research. Yeah, this the most popular liquid chromatography chiral surface, the CSP type. The first one is using the cyclodextrin. The characterization of the CD is CDKPT contain hydroxyl for H bonding with polar group of analyte. Hydrophobic portion of analyte fit into non-polar KPT. So we name the we get this inclusion complex. The symbolic column is cyclobond, the name of the type of the chiral column. And then the second one is the protein base. Natural protein bonded to a silica-metric protein contain large number of chiral centers and interact strongly with small chiral analytes through hydrophobic and electrostatic interaction, no side bonding. So the symbolic column is the chiral AGP. So we have to this column, cyclodextrin and protein base in our laboratory. And the third one is the polysaccharide, enantiomer from H bond with carbamate link between side chain and polysaccharide backbone, the chiral part. And then the last one is the brush type based 3-point interaction principle for chiral discrimination, the symbolical the YO1. The previous study about the chiral special preponage using the brush type. So ladies and gentlemen, this one the mechanism of CSP interaction with the analyte. There are 5 types. The mechanism of the interaction between the chiral surface CSP with the solid or analyte. Type 1 is the CSP resolved enantiomer by establishing 3-point interaction. And then the second one, chiral discrimination by type 2 CSP involve a combination of attractive interaction and inclusion complexing. There are linear polysaccharide derivative. The type 3 is the based on special solid interaction with chiral activity to form inclusion complex. So this including cyclodextrin and cyclization derivatives. The type 4 is the CSP form diastereomic metal complex with chiral analyte by means of chiral ligand exchange chromatographic or CLEC mechanism. And type 5 CSP are proteins interaction with the solid are a combination of hydrophobic force and hydrogen bonding. This the mechanism of this CSP interaction with the analyte in HPLC method. So this the HPLC instrument maybe we know this instrument of the chromatographic method. So this the result the previous study on the non-expression of ketorolac by HPLC using AGP as chiral column, the protein base. This one the ketorolac, it has 1 chiral center, so it has two enantiomers. We get the baseline inspiration more than 1.5 resolution. Also, we have developed the determination of the ketorolac in the pharmaceutical sample using the tablet sample, chromatogram using the AGP chiral column 10 cm, HPL condition using the mobile phase 100 millimolar phosphate buffer without organic modifier. Yes, this is the flow rate 0.7 milli per minute, injection volume 5 milli, and also using the UV detection at 322 nanometer. And then this one, the result for the non-expression of ibuprofen by HPLC using the AGP as chiral column. We get the baseline expression for the ibuprofen. Has also the 1 chiral center, so we get the 2 peak of enantiomers. Yes, similar with the ketorolac. Yes, 100 millimolar phosphate buffer, flow rate 0.7, injection volume 5 milliliter, and microliter, and also euphoration at 2 to 5 nanometer. And then this result for the non-expression of iconazole by HPLC using cyclobond as chiral column. So different chiral column. Yeah, this is the cyclobond, the cyclodextrin base of the chiral sulfase. This one, the iconazole, it has one chiral center, so we get the 2 peak of enantiomers using the standard solution 100 ppm, and also we have developed the determination of the pharmaceutical sample, liquid sample for the analysis of the iconazole sample. The condition, the SPLC using the Aztec cyclobond column, yes, 25 cm. The condition of mobile phase composition is 0.2% formic acid in water with composition acetonithyl 20% and then water 80%. Flow rate 1 ml per minute, injection volume 1 microliter, and UV detection at 220 nanometer. So this result is in preparation, yeah, or in submission process to the international journal. So this last out of my presentation, maybe this time is limited. Our research in progress, collaboration with Gajah Mada University, with Prof. Mudasir, and also the research in magister student in Gajah Mada University for the molecular docking study for prediction of chiral expression of selected drugs, namely ketorolac, ibuprofen, hydroxychloroquine, and etc. In the field of molecular modeling, docking is a method which predict the preferred orientation of one molecule to a second when bond to each other to form a stable complex. So this the result. It will be presented in the internal seminar. Molecular docking of the prediction of the non-transparent of the ketorolac, ibuprofen, and also hydroxychloroquine, the antivirus drugs. The closing remarks: the non-transparent of selected chiral compound using CE and SPLC have been successfully developed. Chiral expression of some triazole fungicide and also azole drugs were successfully achieved by CDMEKC method, a mode of C technique. The migration behavior of the individual non-tom is determined by their competitive equilibrium between the aqueous phase, micelle, and cyclodextrin. The electrolytic interaction, hydrophobic interaction, hydrogen bonding interaction between the selected chiral compounds and cyclodextrin play a critical role in the chiral recognition mechanism. And the last one is the HPLC method was also applied for the chiral expression of selected chiral drugs, namely iconazole, using the cyclodextrin-based phase, CSP. In addition, chiral expression of selected non-steroidal anti-inflammatory drug such as ibuprofen and ketorolac was achieved using the protein-based chiral synthesis or IgP column. And then the presented method have been also successfully applied for the determination of the selected chiral drug in the pharmaceutical sample. This one, the acknowledgement for my supervisor in UTM during my PhD and also postdoc, Prof. Wan Aini, Prof. Muhammad Marsin, and also Prof. Hasan Wa'ibunen, my colleague from the AG. Also, he is the one of the visiting professor in the General Sudirman University in 2016, I think, yeah. And also Prof. Mudasir from Gajah Mada University, Research Group of Organic Chemistry Laboratory, Department of Chemistry, General Sudirman University, and also Ministry of Education, Culture, Research, and Technology Republik Indonesia for the research program of the world-class research. Thank you very much, Dr. Roy Andreas. Time to finish for my presentation. Thank you.
Okay, thank you very much, Mr. Dadan Hermawan. It is also very interesting presentation, I think. And then even you still present your research, there is so many questions already.
Yes.
Yeah, that means this presentation is very, very interesting.
Yes.
So, Mr. Dadan, if it is possible, maybe I can put all these questions after the third presenter. Is okay? Okay.
Agree. Yes.
Okay. To effective our times, so let us to continue for the third presenter, and then after that we put all question after all the speaker finish their presentation. It's okay?
Yes.
Okay. Thank you, Mr. Dadan Hermawan.
Thank you very
And
much.
let's continue. Give applause for Associate Professor Dadan Hermawan.
Thank you.
Okay, we will continue for the third presenter. Good morning, Professor Won Kuli, or maybe it is okay for me if I say Professor Lee is okay?
Yes, thank you.
Okay, thank you so much. Yes. Good morning, Professor Lee. Professor Lee is, maybe before we see the presentation from Professor Lee, please let me to read a brief profile about him. Professor Won-Koo Lee, or Professor Lee, is professor at the Department of Chemistry, Sogang University, Korea. Bachelor degree in chemistry, February 1984 from Sogang University, Seoul, Korea. And then magister in chemistry on the same university, Sogang University, Seoul, Korea. And then PhD in chemistry from University of Illinois at Urbana-Champaign, USA. So actually, I really want to study there, but it's difficult, right? It's difficult to enter to this university. Okay, and continue. From 1993 to present, Professor Lee is the full professor on the Department of Chemistry, Sogang University, Korea. And also he has some experience like a visiting professor at University of Illinois at Urbana-Champaign, and then also another experience, also director of research affairs, Sogang University, and also maybe 2000 is got like Alexander von Humboldt Fellow, something like that, from Max Planck Institute, Germany. The current research interest is developing new synthetic methodology using chiral aziridines. And then the second one is synthesis of biological active nitrogen containing compounds alkaloid, and also synthesis of unnatural amino acid and their derivatives. Okay, to shorten the time, Professor Lee will be present his research entitled "Can we design organic reaction environmentally friendly?" Oh, this is very nice question, right, Professor Lee? Very nice question. So we will listen together presentation from Professor Lee. Now time is yours.
Thank you so much, Dr. Andreas, for nice introduction. And I'd like to thank Professor Anung and all the organizing committee for inviting me to this wonderful joint conference today. I feel so sorry I cannot be there because I used to visit Yogyakarta 8 to 10 times a year, every year. But since last year, I cannot travel to Indonesia due to this corona pandemic. So maybe I wish I can travel to Indonesia soon and meet everybody, in person. So let me share my slide here. So everybody can see the slide. Is it okay?
It's okay.
Okay.
Great. Yes.
Good. Okay, the title of my talk today is Can we design organic reactions environmentally friendly? In the previous slide, in the previous lecture, Professor Hermawan also mentioned about the wonderful separation science using capillary electrophoresis. And he mentioned about minimum use of organic solvent and minimum production of the waste. So he is in separation science and I am in organic chemistry. In these days, many chemists, whatever the field is, are aware of using organic solvent, how much solvent we use, okay? Because if we use organic solvent in the reaction, after the reaction, we have to remove all the solvent, or we have to recycle it. That takes a lot of time and it costs a lot of money. And it usually is not good for the environment. I've been working in this area for almost 30 years. And I used a lot of organic solvent. I produced a lot of waste, you know, in my life as an organic chemist. So for the last 10 years or so, I tried to design organic reactions which can be environmentally friendly, because I thought it's about time for me to pay off, you know, for the last 30 years of my committing sins for the environment. So the question is, why are we interested in this topic? If we take general public and ask them question, how they think about chemistry, then probably they would say chemistry is not an environmentally friendly science, because they can see smokes are coming from the factory, and they can see the polluted water is coming from the factory, which can pollute the river, pollute the ocean. Okay? So that's everything they see about chemistry. So generally, chemistry is not considered as environmentally friendly science because it produces polluting material. In organic chemistry, how do we run chemical reaction? The chemical reaction is usually in solution-based chemistry. Okay, that means we put reacting material, which is a solute, and we put solvent. Every time we design organic reactions, we take some time to think about which solvent would be the perfect solvent for the reaction. Because the role of the solvent is mixing the reacting material in one phase so that the molecules can move freely. Then they can collide to generate the reaction. That is what we teach in physical chemistry for the undergraduate students. Okay. If we remove the solvent from this reaction system, then the solute itself cannot move freely. So they cannot making collisions. And if there's no collision between the molecules, there's no reaction. Okay. So why we think we need organic solvent in the reaction? because we know that from the history, we learned some lessons. Let's compare the grapes, okay? Crushed grapes can produce wines, but dried grapes, whatever time, if you wait for a long time, 1 year, 2 years, there's no change. Dried grapes is dried grapes, right? No changes happen. How about milk? Milk can turn into cheese. We can make a butter. We can make a yogurt. We can make creams. But with dried milks, no change at all. The dried milk does not change to anything. So from this kind of experience, conversion of one material into another material, we need a liquid, right? But nothing happens in solid state. So the great philosopher Aristotle said, "Nou corporis fluida." If there's no liquid, there's no reaction. Okay, so this is the lesson we learned from the history. So every time we design chemical reactions, we think of solvent first. Okay? We need some liquid to mix the reacting materials. Now, let's talk about environmentally friendly chemistry or green chemistry. Environmentally friendly chemistry means maximize atom economy. We do not want to lose any atoms from the reacting material. So we want almost all the atoms present in the starting material is going to the product. Or we want to minimize the use of solvents, minimize the use of energy, and we want to produce minimum waste, as Professor Hermawan just talked about in the previous lecture. And the part of the theme of this joint conference is education for a better future. Okay, we want to leave a better environment for the next generations. We do not want to ruin the environment. Especially in Indonesia, you have a wonderful natural resources, and you do not want to ruin those wonderful natural resources. So there has been a lot of efforts to design environmentally friendly organic chemistry. And I want to present some examples today. So the first reaction I'd like to talk about is atom economical synthesis of oxyindole from this aniline derivative. We have the starting material here, and we use transition metal oxide nanoparticle catalyst, just 5 mole%. And we heat the reaction mixture 5 to 10 hours in the air, right? This is the open air reaction. And the starting material turns to the product almost quantitatively. We have very high chemical yield in this reaction. So what's in the reaction system here? We have a starting material, which is a liquid, okay? And we have a solid catalyst. and nothing else. We do not have any solvent in this reaction system. So what's happening in this reaction? In this reaction, we are making new carbon-carbon bond between this carbon and this carbon. This is a new carbon-carbon bond formation between this carbon and this carbon. Okay? So what is happening in this reaction? This is a truly solvent-free reaction. And the catalyst we are using, we can use many kinds of transition metal oxide here. And copper oxide is just one example. And copper oxide is a very cheap transition metal oxide. Okay. And let me show you the reaction system. This is a typical synthetic procedure. In the reaction vial, we have a glass reaction vial here, and we put substrate, the starting material here. Okay, we have starting material, and we put copper oxide nanoparticle as a catalyst. Then put this reaction vial to the aluminum block. And we have a temperature controller here. And we have a heater so that we can control the reaction temperature. So there's no cap because we need air. And we just heat the reaction mixture here. Then the reaction is going complete to transformation of the starting material into the product. There is no side product, okay? So all the starting material is changing to the cyclization product. Okay. Let me show you some reaction results. So these are results here. So we have a couple of the product and the reaction yield. You see the reaction yield is almost quantitative. Okay, no waste is produced, no side product is produced. We get only this cyclization, intramolecular cyclization product. For this reaction, we need some requirement. We have an acidic proton here. We have a proton here. And we need some electron withdrawing group for Al2 or Al3. So Al2 may be another carbonyl group or cyano group, so that we can make this proton acidic. Because we know the transition metal oxide is a weak base. So it can remove the acidic proton at the alpha position of this carbonyl group. And I will show you the proton NMR of the crude product, crude reaction product, this one. Okay, this is the crude proton NMR. Okay, it's very clean. We have an N-methyl here. We have 3 vinyl protons. We have 3 vinyl protons here in the allylic group. We have an ester here and here. And we have 4 aromatic proton here. So for the crude product NMR, this is very clear, right? That means there's no side product. And in this organic transformations, we don't need any extraction. We don't need any chromatography. Okay. And in the reaction, we did not use any organic solvent. So there's no chance for losing product by further purification step. I'm sorry to Professor Hermawan, who is in separation science. We don't need separation here, okay? Because we do not have the multiple products from this reaction. So one starting material goes to one product. Okay. Some people reported the synthesis of this natural product, horspilline, from this starting material. And he prepared this starting material using different method. And we showed we can prepare this compound just in one step from this starting material in a very efficient way and very environmentally friendly way, without using any organic solvent. And the chemical yield is 97%, which is a wonderful reaction. Okay. And what's happening in this reaction? How can we explain this reaction? This is the explanation we provide. As I mentioned in the previous slide, the transition metal oxide can act as a weak base. Okay? So we used copper oxide in this case. So this transition metal oxide remove this acidic proton here to generate an anion, which is a very stable carbon ion, which can be stabilized by 2 carbonyl group at both sides. So the acidity of this proton is about 10. The pKa is a little bit less than 10. So the first thing happening here is the deprotonation of this acidic proton by a copper oxide to generate carbon ion. Then there's a 1 electron oxidation by transition metal to generate this radical. Then this radical cyclized to the aromatic carbon suspension system to make a bicyclic structure to generate the aromatic radical here. Then this radical is further oxidized, 1 electron oxidation by a transition metal to generate this carbocation, aromatic carbocation. Then removal of this proton by metal oxide to generation for the generation of this aromatic ring structure. This is the sequence of the reaction. Okay. Then the transition metal was reduced by 2 electrons here. Then we have to reoxidize the reduced transition metal. That's where the air can play the role. The oxygen in the air can reoxidize the reduced transition metal here. That's why we need air, right? So we need an open air system here. How did we know we need an air in this reaction system? Because we did run this exactly same reaction in an inert atmosphere under nitrogen or under argon in a glove box. Then there's no reaction. No reaction is going in the glove box. So that means we need an open air system. We need an oxygen. We need oxygen to reoxidize this reduced transition metal. Okay, so we developed this environmentally friendly intramolecular cyclization reaction to prepare this kind of bicyclic nitrogen-containing product. And we reported this reaction in Green Chemistry. Okay, the name of the journal is Green Chemistry, which is very nice, right? Now, can we extend the ring size using this reaction? Yes, we can. We can put another carbon between the aromatic carbon and the nitrogen. So we put a keto group. Then we did the same reaction using copper oxide nanoparticle. And we added 1 drop of acetonitrate as a solvent. In this case, this starting material is a solid and catalyst is a solid. So between those two solids, there's no mix at all. So we need something to mix the starting material, solid starting material, and the solid catalyst. That's why we add 1 drop of acetonitrate. Then heat the mixture to 70 degrees. Then there's a very nice transformation of the starting material through the same mechanism, through the 6,6 bicyclic compound and very high yield. So we can prepare this kind of isoquinoline ion system using the intramolecular cyclization reaction. Okay, this is just one example of environmentally friendly organic reactions. Okay, let's change the topic here. This is hydrogen. Right? This molecule is hydrogen. Hydrogen is very toxic material and explosive material and very corrosive material. Hydrogen itself is a liquid, but we can usually get hydrogen as an aqueous solution, 10% to 20% aqueous solution. There is no neat hydrogen because that neat hydrogen is a very dangerous material to deal with. The one guy in my department found out if we react aqueous hydrogen with supercritical carbon dioxide, we can prepare this hydrogenium carbamate salt. This is a solid. This material is solid. It's very stable. So this material is a solid neat hydrogen. And if we heat this solid material to 60, 70 degrees, there is a decarboxylation reaction to give the neat hydrogen. Okay, so if we react this solid material with various carbonyl compounds, we can produce condensation product. We can make this pyrazole system, cyclization reaction between hydrogen and this dicarbonyl compound to make a 5-membered pyrazole compound. And we can make also 6-membered ring product. We cannot do this reaction with aqueous hydrogen, but we can do this reaction using this neat solid hydrogen. Now, the solid hydrogen carbamate looks like this. This is a white crystalline compound. in the reaction, how we do the reaction is like this. Okay, here's solid hydrogen, and here's a dicarbonate compound. This is a solid, and this is a liquid. So we mix these two compounds 1-to-1. Mixture is ground, right? Then heat the mixture. Then upon heating, there's a decarboxylation reaction is taking place from this solid to generate neat liquid hydrogen. Then the liquid hydrogen reacts with this bicarbonate compound to have a condensation product here. Okay. So in this reaction, also, there is no organic solvent is involved. So this reaction is absolutely solvent-free reaction. So this is some examples of pyrazole synthesis. The chemical yield is very high. This means there's no side product. It's a very clean reaction. Okay. And here's one more example of the solid amine process. Usually amine compound, a liquid, right? And amine has an unpleasant odor. The smells is really bad. Some people do not like fish because fish smells. The fish smells are coming from amine compound. And liquid compound has a handling problem and weighing problem. Weighing the liquid compound is not easy. So if we can convert this liquid amine into solid, it will be much easier to handle. And there's no smell from this solid amine compound. So if we react this amine with carbon dioxide, we can easily prepare this ammonium carbamate salt. This is a solid. In this case, we have 2 amine in 1 carbon dioxide. So 2-to-1 salt. So this is the chiral primary amine, S-phenethylamine, and this is the solid product, this one, ammonium carbamate salt. How can we prepare this solid amine? This is a short movie, but seems like I cannot. Oops. I'm sorry. Seems like do not play this movie. In this movie shows how can we prepare the solid amine from the liquid amine using dry ice, which is very simple. And this kind of reaction can be used for the separation of this mixture. Let's say we have a mixture of liquid amine and liquid alcohol, 20-to-1 mixture. Let's say we have this 21 a mixture of amine and alcohol. These 2 compounds are liquid. So only way we can separate these 2 compounds is chromatography, right? if we do the chromatography, we have to use a lot of organic solvent here. But if we react this mixture, liquid mixture, with carbon dioxide, only amine compounds react with the carbon dioxide to make this 2-to-1 salt, which is a solid, and the alcohol compounds do not react with carbon dioxide. So this decanol, alcohol, stays as a liquid, and amine is converted to solid, right? So we can filter this solid. Then in the filtrate, there's only this alcohol compound, right? So we filtered this solid. Then we took an NMR, proton NMR. There is no decanol, there's no alcohol, and we have only this T-butylamine in the solid, right? And in the filtrate, the NMR of the filtrate is only 1 decanol. There's no amine is left here. So doing this carbon dioxide chemistry, we can easily separate from amine compound from any other contaminants. So this chemistry can be used for purification, or this can be used to elimination, for the elimination of the amine compound from the mixture, and etc., etc. So this kind of chemistry can be used in various fields of organic reactions. And let me show you how can we use this solid amine compound. Okay, this salt, ammonium carbamate salt, is formed from the reaction of chiral amine and carbon dioxide. Okay. So we can use dry ice as a carbon dioxide salt, as a source. Now, this is a solid, so it is very easy to weigh the compound. We can weigh exact amount of the amine by using chemical balance. And if we react this solid with aromatic aldehyde with no solvent, because aromatic aldehyde are liquid, okay? So this aromatic aldehyde is acting as a solvent and also as a reactant, right? So this is a solid and this is a liquid. So no solvent is required in this reaction. Then we heat the mixture. Then when we heat this carbamate salt, there is decarboxylation is taking place, and we generate the liquid amine slowly. Then the liquid amine react with this aldehyde to have a condensation product, which is an imine. Then we can reduce this imine to the corresponding amine compound. This whole process is called the reductive amination reaction. Okay, so we can do this reductive amination reaction without any organic solvent. Okay, so this is how we do the reaction. So when we heat the mixture, you can see there is a water droplet here, right? From the condensation reaction, from amine and aldehyde. When condensation reaction is taking place, we generate water. So the formation of this water droplet means the condensation reaction is going smoothly. So after the condensation reaction, we put some hydrogenation catalyst here, then put hydrogen balloon there. Okay. Then we can reduce the carbon-nitrogen double bond to have the reduction. we can also do the reductive amination reaction with aliphatic aldehyde too. So from this aliphatic aldehyde, we obtained a reductive amination product in very high yield. Okay. So heating the mixture to 50 degrees Celsius in 1 hour, and using the platinum oxide catalyst for the hydrogenation reaction in the second step, we produced this reductive amination reaction. Also, various aromatic aldehyde can provide this reductive amination product in very high yield. Okay. In terms of the hydrogenation catalyst, we tried many catalytic systems. We used platinum oxide, which is a little bit expensive, or we used the platinum on carbon or palladium on carbon, and we also used sodium borohydride for the reaction of carbon-nitrogen double bond. In terms of the reaction time, the sodium borohydride takes only 30 minutes, half an hour, but the yield is a little bit lower. If you can stand 7 hours, we can get a better yield. Right? So setting up the reaction and take your time, relaxed. I know most of the Japanese people are very relaxed people, right? So you can stand 7 hours, then we can get a very high chemical yield here. And this reaction is also reported in 2014. Okay, this is the last example of the solventless organic transformation, pyrazole synthesis. I've been working on aziridine chemistry for a long time, usually chiral aziridine. But this aziridine is not a chiral aziridine. Okay? So this is a keto aziridine compound. And we react this carbonyl substituted aziridine with substituted hydrogen. And we use 1 drop of phenol. Okay? Because in this reaction, we need an acid catalyst. So this 1 drop of phenol is solvent and also can be an acid catalyst because the phenol has acidic proton, pKa is about 10. Then the mixture is heated. Then we produce very high yield of this pyrazole compound. Now, how does reaction happen here? The heating of this carbonyl and hydrogen gives this hydrogen from the condensation reaction between this amino group and this ketone, okay, to formation to form this hydrogen. So removing 1 molecule of water gives this hydrogen. Then the protonation of this nitrogen from this phenol proton gives aziridinium ion, which is a very good living group. Then there is an intramolecular cyclization reaction between this nitrogen and the carbon, which produce this 5-membered ring system. Then another protonation on this nitrogen, then removing this amino group to produce carbon-carbon double bond here, provide this pyrazole final product. Okay. So in this reaction also, we did not use any organic solvent. Okay. So it's a pity we used 1 drop of phenol. So please allow me this 1 drop of phenol. Okay. If you insist this is a solvent, again, I don't have anything to say about that. But if you allow me, just one drop of one drop of liquid is okay. So we can say this is a solventless organic reaction too. So using this solventless, solvent-free organic transformations, we can prepare many kinds of nitrogen-containing compound. So the conclusion of my talk today is we developed some organic reactions, some environmentally friendly organic reactions. And those reactions are atom economical, one-part reaction, and it is very high yielding pathway for the product. And again, I'd like to thank you for your attention, and thank you very much for inviting me to this wonderful conference. Terima kasih.
Thank you so much, Professor Lee. This is also very interesting presentation. Before you finish your presentation, there is already some question for you. Okay.
Okay.
So that means this. Oh, Professor Lee, one of my children like to see Korean pop, something like that. Oh. And then she told me, if I saw with you, please tell to Professor Lee, Hamsaheo.
Oh, thank you.
Thank you so much. Okay.
Yeah, that
okay.
Yeah.
Yeah. Okay. Thank you so much for your great presentation. So now times for discussion. So just like I told you all participants before presentation. So if maybe some of you want to ask question, you can directly raise your hand. And also maybe you can chat your question on the chat column, something like that. Okay, please. Now maybe I will give for the directly question. Maybe someone want to raise hand, maybe something like that. Okay. Before I read, maybe some question from the chat column. So first, maybe someone want to ask directly. Question directly, please. Oh, okay. Yeah, maybe still preparing, something like that. So now there is some question. Maybe first for Mr. Dadan Hermawan. There is some question. So many questions.
Oh, okay.
So many questions.
Yes, yes.
I think first for Dadan, Pak Dadan Hermawan, Mr. Dadan Hermawan, this is some question. Maybe number one is from M. Khalid. Number one is, will CE will develop to be CE preparative like her or brothers, SPLC preparative? And how can, especially how separate between CD, MEKC, and enantiomer, something like that. Please, maybe you can answer this question.
Okay, thank you, Dr. Andreas, and also the participant. This is the important of the question, because CE or capillary is only for analytical separation, cannot be used for the preparative separation. Maybe HPLC can be used for the preparative separation because the volume, the injection of the sample is the limitation of the CE for the volume sample only nanoliter. That's Dr. right for the first question. Yeah.
Okay. Yes. Okay. Now is continue maybe for the second from Salsabil Rahmadina from Jenderal Sudirman University. I want to ask, the separation of chiral compounds can be used by SPLS LC method, and why you choose CE method? What the considering?
Yes, thank you for the nice question, from Salsabil, my student in chromatography course. Maybe in my preliminary presentation, yes, I mentioned that CE has many advantages. For example, CE only nanoliter sample volume. So the Prof. Wan Kohli mentioned about the green chemistry or the environmentally friendly method. So the only nanoliter sample volume. Also, little use of hazardous organic solvent. So it is environmentally friendly, and also minimal use of expensive chiral selector, and also short analysis time. So this the many advantages of the CE compared with the HPLC, but also maybe the limitation of CE is only for the analytical expression. Yes, the HPLC is also have the advantages about the sensitivity, and also the can be used for the preparative expression. That's Dr. Roy. Yes.
Okay, thank you so much. Maybe next is the question. Maybe next, please help me to see the question for Professor Lee.
Okay.
Maybe just change. Okay.
Yes.
Maybe there is another before continue for the Mr. Dadan. It is possible to
Yes,
show me. Okay. Okay, this is for Professor Lee.
Okay.
First question is from Waroni from Jember University. Overall reaction to oxidazole via cyclization reaction and the proposed reaction mechanism. One is carbocations, and second is aromatic. In aromatic side, it very rich electron also that the migration from aromatic to carbocation to product oxidazole compound via cyclization reaction. Maybe this is the first question. Maybe Professor Lee, can you catch the questions?
So probably he's talking about the mechanism of the cyclization reaction here.
Okay. Okay, please, Professor Lee, maybe you can give us some explanation about this.
I'm not sure this kind of mechanism works.
Okay.
So I proposed that the cyclization reaction is a radical process. Okay. Usually, radical process is not affected by the electron density in the aromatic ring system.
Okay.
So he can say that, but our radical mechanism also can be plausible for this reaction.
Okay. Okay, thank you very much for your comment. And then maybe we are continue for the second question is from Pratama, Chemistry Department, Diponegoro University, Indonesia. Dear Professor Lee, it is very nice presentation. I'm inquiring about what is the energy that enable two compounds can react to each other when no solvent employed. Yes, without solvent, right?
Yeah.
In my opinion, just in the gas phase with the high pressure and temperature, the two compounds will be able to react each other if no solvent is employed. Okay.
It's a very good point.
Please.
Yeah, it's a very good point. So usually in the gaseous phase, okay, there's no solvent. The gaseous reactant can move freely in gaseous phase. But in the gaseous phase, reaction is usually an industrial process because we need high pressure and high temperature. So we cannot use that kind of reaction condition in the lab. Okay, so we have to compromise the 1 atmosphere pressure, and maybe we can compromise the temperature, maybe 200 degree, 150 degree, but the problem is the material, the starting material and the product should be stable up to the high temperature. Okay, even though we did not use any organic solvent, the role of the solvent is just for mixing of the reacting material. Okay, but if 2 reacting materials are liquids, we don't need any more organic solvent, because a liquid mixing is can happen or when we raise the temperature. Or the reacting material, if the reacting materials are 1 solid and 1 liquid, the liquid reacting material can act as a solvent and also as a reactant. So liquid solid system also works. Okay, so we think theoretically we don't need any more organic phase if we have a liquid or liquid solid. But as I mentioned in my lecture, if we have a 2 solid phase reactants, there's no mixing between 2 solid phases. Okay, then we need something to mix those 2 solid materials. That's why we added a little bit of liquid, couple drops, 2 or 3 drops acetonitrile in this case. So if this can be an answer for the person who raised the question here, that's my answer.
Okay, thank you so much. I think we are already understand what you means, and then we can come back to Mr. Dadan Hermawan. Okay. For the next question, number 3, from Rafif Alvarez from Jenderal Sudirman University. According to Salsabila's questions, is there any effect when we use CE to separate chiral compound instead SPLC?
Okay, thank you for the question. I think there is no side effect. Okay. Rafif, yes, it is environmentally friendly. So this is my experience. I have used the CE about 10 years. So until now, I healthy. There's no side effect of the CE instrument. So maybe CE use the applied voltage until the 30 kilovolt. So this 30,000 volt. So maybe the high voltage, but there is no side effect. I have used the CE instrument about 10 years. There is no side effect. Thank you.
Okay, I think it's very great method.
Yes.
Okay, now maybe the 4th question is, maybe before continue, maybe someone want to ask directly, maybe raise hand. Someone want to ask question directly. So I will give a chance, something like that. Still now, okay, we will continue for the 4th question from Khaliza Sia, same from Jenderal Sudirman University. Maybe it was mentioned the using of the surfactant in separation process. Is there any certain properties the surfactants should have to be used in separation process? And what kind of surfactant used in your research? Please, Mr. Dadan.
Okay, thank you very much, Doctor. This is a very good question from Zia. Yeah. So in my research, I use the SDS, sodium dodecyl sulfate is the anion surfactant. So SDS is the family of the organosulfate compounds. Yes, and then CMC, the critical micelle concentration of the SDS is about 8 millimolar. So this is the what the certain properties. Yeah, we use the surfactant with the low CMC maybe. So we can use the 10 millimolar or maybe 20 millimolar of SDS in my experiment. This the one of the properties. So maybe we can also use the other surfactant, and maybe we can compare the result. But the question is, can we use the other surfactant, and then we get the best non-expression. For example, the higher the resolution, and also the low faster analysis time, and so on. So that's about the SDS. Thank you, Dr.
Okay, thank you so much. I think this is very clear answer. I think something like that. And then maybe back to Professor Lee, please.
Okay.
Okay, the next question, number 3. Okay, this is Mr. Waton. I was wondering, when you perform the reaction using this catalyst, copper oxide, did you recollect and then reuse the catalyst?
Yeah.
And then the second question is, yes, I think this is very interesting question, right, Professor? Because I do also the same like this research.
Yeah, have we recycled the catalyst, copper oxide catalyst?
Yes.
Yeah, we can recycle the catalyst, of course, but the copper oxide is not an expensive catalyst, so we didn't take time to recycle the catalyst, but theoretically we can recycle the copper oxide catalyst. And I just showed you copper oxide case, but we can use a zinc oxide, we can use iron oxide, we can use a bunch of transition metal oxide, and all those transition metal oxide works nicely in this system.
Okay, and continue from the same persons. That is really interesting to obtain the product was high yield, more than 90%, something like that, without even using a solvent in the reactions. I was wondering if there were any limitation to perform of this reaction, limitation for this reaction.
Yeah, it's amazing to obtain very high yield of the reaction from this reaction system. And I don't think there's no limitation to perform this kind of reaction. And one good thing to remove the organic solvent from the reaction system is the reaction vessel. We can reduce the reaction vessel size.
Okay.
Right? Maybe let's say in chemical industry, maybe I wonder, have you seen the real reactor in the chemical industry? The reactor size is huge, right? 20,000 liter reactor or 50,000 liter. It's a 2-ton or 5-ton reactor to react 100 kilo of the starting material, right? We need a big reactor. But if you can remove the organic solvent from the reaction system, we can decrease the reactor size. So we don't need a big reactor, okay? So we can do the chemical transformations in a smaller size of the reactor. Okay, that is one good thing to remove the organic solvent from the reaction system. And if you are clever, then you can design this kind of solvent-free organic reactions. Then you can contribute a lot for the environment, right? And it's very economical. So in terms of economy, and this is very useful reaction. So you can expand the scope of this kind of reaction.
Okay. Okay, thank you very much for your clear explanation. Maybe continue for the next question from Mr. Pasarwan Siahaan.
Okay. Yeah, kinetic
on
theory.
Yes,
Yeah.
on the kinetic theory, the molecule should be moving to
Yes.
interact each other. How
Yes.
this can be happen on the solid phase?
Oh, yes.
Is the requirement?
Oh,
Yes,
yeah.
this is very good question,
Yeah.
Professor.
Yeah. As I mentioned in the slide, between solid, right? There's no mixing, right? That's why we need a little bit of liquid to make them mix. Okay. So in the solid starting material and solid catalyst, we used maybe 2 or 3 drops of acetonitrile solvent to mix those two solids, so that we can provide the surface to meet those solid to meet, so that the reaction can happen. Okay, so if we do not use any liquid, the reaction maybe can be very slow, or the reaction does not taking place. Okay, so that's why we need just a minimum amount of liquid phase to mix those two solid systems. It's a very nice question, but there is some examples. The reaction between solid is taking place, okay, between the surface. Okay, we have one solid here, another solid here, and there is a surface between those two solids, and reaction can take place in the surface contact area, but the kinetics is very slow. So that's very good point, right? So to solve the problem, we need a little bit of the minimum amount of liquid, so that we can facilitate the reaction process.
Okay, thank you so much. Maybe before we go to next question, maybe there is a give chance again to someone want to ask a question directly. Okay, please. Maybe someone want to ask directly question. Okay. Oh, still. Okay, continue. Maybe before we go to Mr. Dadan, there is please to Mr. Dadan. There is so many questions, Mr. Dadan.
Yes.
Mr. Dadan. Yeah.
Okay, please, Dr. Rai.
Yeah. Okay. Continue for the number 5 from Busroni. Yes. What is the definition? Maybe definition, right?
Yes, yes.
Definition of chiral and achiral, and also enantiomer in the material prophylacenozel, and how to separation of propiconazole and each enantiomer from propiconazole, something like that. Maybe.
Okay, thank you. Okay, thank you, Dr. Rai. Thank you, Dr. Busroni. He is my best friend from Jember. Thank you, Dr. Busroni, for the question. Okay, the chiral, so maybe in organic chemistry is the very famous, yes. The chiral carbon is an asymmetric carbon. So a carbon atom can have a maximum of 4 bonds, and the chiral carbon is bonded to 4 different groups. Therefore, it's asymmetric. So this is the term of the chiral carbon. So many definition about this chiral. So what is the achiral or non-chiral is if the carbon atom have the not different atom in 4 bonds, maybe similar 1 or 2, maybe 3. Okay. And then how to separate the enantiomers propiconazole from we have explained before. So in the CDMEKC method, we can separate 4 peaks of enantiomers of propiconazole, pairs of 2 pairs of propiconazole, because propiconazole have 2 chiral centers. Yeah. using the Hsp gamma CD as chiral selector and using the SDS as micellar base. Yeah. So the MEKC or CDMKC is the hybrid of the electrophoresis and chromatography methods. So it's called the pseudo standard base. Yes. Yeah. Then in the CDMKC, the migration behavior of the individual enantiomer is determined by their competitive equilibria within the equispace, the micelle, and the CD. So we should optimize this buffer or the background solution. So we should optimize the micelle concentration or the type of the micelle or surfactant maybe, and also should screening of the base of the CD for the chiral selector, many type of CD, cyclization, and also the base concentration of the cyclization for the base resolution of the enantiomeric separation. That's all, maybe Dr. Rai. Thank you.
Okay, thank you so much, Dr. Tedan Hermawan. Next, maybe one more question, maybe.
Yes.
From Agni Lili. I think I know her.
Yeah.
I think this is my student now.
Yeah.
Continue for doctoral course in Japan.
Okay, very good.
Okay. May I ask, will different mobile phase ratio change the absorbance or maybe the detected area within the retention times?
Yeah.
Something like that. Okay.
Yes. Okay. Thank you, Dr. Rai. Okay. It's correct. Yeah. Yeah. The different mobile phase ratio could change the retention time, or migration time in CE, and also resolution with the two analytes, and also maybe it could affect also the absorbance and also the detected area. So it's you should optimize the best ratio of the mobile phase to get the higher resolution, the highest resolution, the lowest retention time, and also the highest peak area or the peak area of the analyte. In my experience, the second question, the column that you use during the analysis. So in CE, I use the capillary. Yes, the polyimide capillary about the 56 cm. Yeah. And then for the HPLC, I use the protein-based chiral column, KP column, and also the cycloban column, the cyclodexin base. Thank you, Dr. Rai.
Okay, thank you so much, Dr. Dadan. And then next is question for Professor Lee. Please help me to change. Okay, next from number 5. First is number 5. Number 5 is from Pertamina University. Prof. Won, can I ask the simple question? Is the column of SPLC has a specific requirement for separation the chiral compounds? Thank you for the answer.
Okay, maybe you saw the reaction system from my slide. Usually, that solvent-free reaction do not produce, other side products. Okay, so it usually provide very clean reactions. So we do not need chromatography. If we need chromatography, then we cannot say it's an environmentally friendly reaction system. So we usually did not use chromatographic separation from the reaction products. Okay.
Okay, thank you, Professor Lee. And next, maybe for the next number 6, for Professor Lee question. Okay, this is from Pratama. However, what about energy drop? The two liquid compound to reacts, and it is just mechanical energy by say Pyrazole, for example.
Yeah, that's a good question. We heated the mixture, right? The energy is coming from the heating, right? Raising the temperature up to 130 or 100 or 80 degree. So heating is the energy source for the reaction. Okay. So heating energy provides the molecule can move, freely, so that there's a reaction taking place.
Okay, thank you so much for your clear answer. I think we still so many questions, Professor Lee and Dr. Dadang.
Yes.
I got from my yes, I saw also from my gadget. I saw some question also. So that's why, but the problem is time is over because the committee already tell me that please, Dr. Roy, time is over.
Yeah.
So,
if there's any more questions, just write me an email. Then
okay.
Okay.
Thank you. Okay, thank you so much. Okay, I think because of times, I think the presentation is very interesting. There's so many questions still cannot answer in this forum. So maybe we can asking later, maybe by email or maybe by directly, something like that. So now thank you so much. Terima kasih untuk Pak Dr. Dadan Hermawan.
Thank you. Yeah.
And then Hamsahyo for Professor Lee.
Terima kasih banyak.
Yeah, because this is very great presentation, very awesome materials that already presents for us. And then before we close these sessions, please, the committee will want to give you a certificate, something like that, certificate for Dr. Dadan Hermawan and also for Professor Lee. Please, can you show us the certificate for the speakers? Okay, this is the certificate for Dr. Dadan Hermawan. Thank you so much for your interesting presentations. And then for the Professor Lee, please. This is the certificate for the Professor Wonku Lee. And thank you so much, Hamsahyo, for your very interesting, very nice presentation and very awesome materials. Okay, thank you so much for all of audience, all of the participants. Now the plenary session 1 is already finished. Then if I have maybe something not good during this forum, so I'm so sorry for all of that. And then now I will give all the time to the Master of Ceremony. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, thank you very much for Mr. Roy Andreas for guiding us in this plenary session 1. Now, it's time to break and prayer session. So, for all of the participants, you can take a break, having a lunch, or do a prayer. But please don't leave this room because we will start the plenary session 2 at 1 p.m. So, thank you and have a nice break.